Hello there and welcome to Science for Sleep, where curiosity slows down for the evening and the universe becomes a little quieter around the edges. Tonight, we're going to spend some time among the stars. Not just one kind of star, but all the strange varieties scattered across the cosmos. Some burn gently for trillions of years, others live fast, shine violently, and vanish before entire planets have time to cool. Some are smaller than Jupiter would like to admit. Others are so enormous that if one replaced our Sun, its outer atmosphere could stretch beyond the orbit of Mars. And despite all of that variety, every single star in the night sky is built from the same basic ingredients: gravity, gas, pressure, heat, time. That's the remarkable part. The universe keeps taking the same raw materials and producing wildly different results. A bit like giving the exact same ingredients to millions of chefs and somehow ending up with everything from soup to wedding cake to something experimental involving dry ice and regret. So tonight we're going to move slowly through the physics of stars. We'll look at how they form, why they shine, why some stay stable while others become catastrophically unstable, and what ultimately determines the kind of object a star will become. Along the way, we'll visit red dwarfs, blue giants, white dwarfs, neutron stars, pulsars, magnetars, and a few other deeply unreasonable things the universe apparently decided were acceptable. Before we begin drifting through all of that though, I'd love to ask you something simple. Where are you listening from tonight? Is it late evening where you are? Early morning? Maybe you're under cloudy skies with no stars visible at all. Or maybe there's a clear stretch of darkness overhead and somewhere above you, hidden among thousands of faint points of light, are stars living completely different lives from one another. And if you find this little journey relaxing or interesting, perhaps while winding down after a long day, I'd really appreciate it if you liked the video and subscribed. It helps this quiet corner of science and sleep reach more people who might want something calm to listen to before drifting off. Now then, let's settle in. Because one of the strangest things about the night sky is how uniform it first appears. From Earth, stars look deceptively simple. Tiny points of white light scattered across darkness. Calm, consistent, almost interchangeable. Human beings spent thousands of years looking upward without realizing that stars could actually be very different from one another. To ancient observers, a star was just a star. Some brighter than others, certainly, some redder, some appearing in different positions depending on the season. But fundamentally, they seemed like fixed lights attached to a rotating sky. That illusion lasted a very long time. Part of the reason is distance. Stars are unimaginably far away, so far that even the nearest appear as unresolved points of light. Unlike planets, which reveal disks through telescopes, most stars stubbornly remain tiny dots no matter how powerful the telescope becomes. For centuries, humanity could only judge stars by brightness and colour, and brightness alone is misleading. A dim nearby star can appear brighter than an enormous distant one. A massive blue star can outshine our sun by hundreds of thousands of times, while sitting so far away that it barely catches your attention. Meanwhile, some stars visible to the naked eye are already dead, their light still crossing space long after the star itself disappeared. That alone is slightly unsettling. When you look at the night sky, you're not seeing the universe as it is. You are seeing delayed information, ancient photons arriving late after travelling enormous distances through empty space. Some of the stars overhead tonight may no longer exist. Their final explosions may have happened before human civilization invented paper, clocks, or reliable bread recipes, and yet their light continues calmly onward. Eventually scientists began noticing patterns hidden inside starlight itself. During the 19th century, spectroscopy transformed astronomy completely. Instead of merely observing stars, astronomers learned how to analyze their light by splitting it into spectra. Suddenly, stars stopped being anonymous points and became physical objects with measurable properties. That changed everything. A star's spectrum reveals its temperature, chemical composition, motion, density, and more. Dark absorption lines pair where specific elements absorb certain wavelengths of light. Hydrogen leaves fingerprints, helium leaves fingerprints, sodium, calcium, iron, oxygen, carbon, all of them quietly announce themselves inside the light. This realization was extraordinary for another reason too. Humans discovered that the same elements found on Earth existed inside stars. The universe was not made of some unreachable heavenly substance. The stars were built from ordinary matter following physical laws we could understand. In other words, the sun was not a divine fire, it was physics. Once astronomers began classifying stars, the diversity became impossible to ignore. Some stars were cool and red, others blazed blue-white at incredible temperatures, some were tiny but incredibly dense. Others were swollen giants with atmospheres so enormous that if placed in our solar system, they would engulf multiple planets. And beneath all those differences sat one central truth. A star's entire life is mostly determined by mass. That's the key to nearly everything we're going to discuss throughout this journey. Mass decides how strongly gravity pulls inward. Gravity determines pressure inside the core. Pressure determines temperature. Temperature controls nuclear fusion. Fusion controls luminosity, lifespan, size, color, stability, and eventual death. Two stars born from the same cloud can end up living completely different lives, simply because one gathered slightly more material during formation. A smaller star burns fuel slowly and carefully. A massive star burns recklessly. The difference is almost absurd. Our Sun, for example, is expected to live roughly 10 billion years. That already sounds enormous compared to human timescales. Entire civilizations rise and disappear in tiny fractions of a star's lifespan. But compared to red dwarfs, the Sun is actually somewhat impatient. The smallest red dwarfs may survive for trillions of years, longer than the current age of the universe by enormous margins. Meanwhile, the largest blue hypergiants may survive only a few million years before exploding. Cosmically speaking, they barely make it out the door. That contrast alone reveals something important about physics. Bigger stars do contain more fuel, but they burn through it disproportionately faster. Increase mass, and the core becomes dramatically hotter and denser. Fusion rates skyrocket. Luminosity rises enormously. A very massive star might contain 100 times the Sun's mass, while producing millions of times more energy. It's less like a larger candle, and more like accidentally replacing your kitchen stove with an industrial blast furnace. And that energy output creates a constant battle inside every star. Gravity pulls inward relentlessly, trying to compress the star further. Fusion pushes outward through radiation pressure and thermal pressure. Stars exist because these forces balance one another. Astronomers call this hydrostatic equilibrium. That phrase sounds technical, but the idea is beautifully straightforward. A star is essentially a long-running stalemate between collapse and explosion. The moment gravity gains the upper hand, the core compresses and heats further, increasing fusion rates until outward pressure rises again. If outward pressure becomes too strong, the star expands, cooling the core slightly and reducing fusion. Stars regulate themselves through physics. Not consciously, of course. The Sun is not sitting there making careful lifestyle adjustments and trying to maintain emotional balance. Though given how often solar flares erupt, perhaps it would benefit from a calmer routine. Still, this self-regulating process allows stars to remain stable for astonishing lengths of time. Our Sun has already existed for about 4.6 billion years, and will continue steadily burning hydrogen for billions more. Every second, though, something extraordinary is happening in its core. Roughly 600 million tons of hydrogen fuse into helium every second. During that process, about 4 million tons of mass convert directly into energy through Einstein's famous equation, E = mc². That energy slowly works its way outward through the sun's interior before eventually radiating into space as sunlight. Oddly enough, the photons bouncing around inside the sun can take tens of thousands or even hundreds of thousands of years to escape from the core to the surface. But once released into space, they reach Earth in just over 8 minutes. So the sunlight warming your face today may have started its journey inside the sun before human beings built the first cities. That's another thing stars quietly do to human perspective. They make ordinary timescales feel very small. Even the youngest stars we'll discuss tonight formed millions of years ago. Some stars visible in the sky were already ancient before Earth developed complex life. Others formed after dinosaurs vanished. A few may still exist long after the Milky Way itself changes shape through future galactic collisions, and despite these incredible scales, the physics governing stars remain surprisingly understandable. Gravity compresses matter, fusion releases energy, pressure balances collapse, mass determines fate. Again and again, the universe repeats these principles while producing wildly different outcomes. Some stars never fully ignite hydrogen fusion and become brown dwarfs, objects sitting awkwardly between planets and stars. Some collapse into white dwarfs supported only by quantum mechanical pressure. Others compress so violently that electrons and protons merge into neutrons, creating neutron stars with densities so extreme that a spoonful would outweigh mountains. Then there are magnetars, where magnetic fields become so powerful they could erase information from credit cards from absurd distances away. Though admittedly, if you are close enough to a magnetar for your banking information to become the primary concern, other problems have probably already taken priority. The point is that stars are not merely glowing decorations scattered across space. They are laboratories of extreme physics. Inside stars, atoms fuse into heavier elements. Carbon forms, oxygen forms, silicon, neon, magnesium, iron. Many of the elements inside your body were forged inside ancient stars long before the solar system existed. That statement has become famous, but it remains remarkable every time you really think about it. The calcium in your bones, the oxygen you breathe, the iron in your blood, all produced inside stars. Human beings are not separate from stellar evolution. We are products of it, and once astronomers understood that, the night sky changed forever. Stars stopped being distant lights and became physical histories. Each star represented a different balance of mass, temperature, pressure, and time. Different kinds of stars were essentially different solutions to the same physical problem. How does matter behave under gravity for billions of years? The answer depends almost entirely on how much matter you begin with. A low-mass red dwarf evolves slowly and conservatively. A high-mass blue giant races toward instability. Intermediate stars like the Sun occupy a relatively stable middle ground. Some stars exist alone. Others orbit companions in binary systems, stealing matter from one another, distorting each other gravitationally, or eventually colliding in catastrophic explosions. Even now, astronomers continue discovering stranger stellar systems, rapid rotators flattened by centrifugal force, stars orbiting black holes, pulsars spinning hundreds of times per second, white dwarfs crystallizing internally as they cool. Yes, crystallizing. There are dead stars in the universe slowly turning into enormous cosmic crystals over billions of years. Physics occasionally sounds less like science, and more like someone quietly escalating a story to see whether anyone objects. But underneath all the strange details lies consistency. The same laws operate everywhere, the same gravity, the same electromagnetism, the same nuclear forces. That universality is one reason astronomy became such a powerful science. By studying stars, humans learned that the universe obeys coherent rules across enormous distances. The physics operating inside the Sun also governs distant galaxies. And perhaps even more comforting, those laws continue functioning whether humans understand them or not. Stars formed long before intelligence evolved here, and they will continue forming long after our species is gone. There's something oddly peaceful about that. The universe is not fragile. It does not require supervision. Stars ignite naturally when enough gas collapses under gravity. Fusion begins automatically once temperatures become extreme enough. Entire galaxies evolve through physical processes unfolding patiently across billions of years. Meanwhile, on Earth, we occasionally panic because a document's saved incorrectly. Perspective can be useful sometimes. As the night deepens and the stars overhead continue their silent work, it becomes easier to understand why people have always been drawn toward them. Not merely because they are beautiful, though they certainly are, but because they reveal something fundamental about reality itself. Complexity emerging from simple rules. The universe does not need separate instructions for every star type. It simply adjusts initial conditions slightly. More mass here, less mass there, and gravity handles the rest. Long before astronomers understood what stars actually were, they noticed something quietly puzzling about them. Some stars looked reddish. Others appeared pale blue or white. A few seemed unusually bright even when positioned far from the horizon, while others remained faint and difficult to see despite clear skies. At first glance, these differences did not seem especially important. Ancient skywatchers mostly treated stars as fixed points, attached to an enormous celestial sphere rotating around Earth every night. That idea lasted for centuries because, honestly, the stars do a remarkably convincing job of appearing permanent. Unlike planets, which wander slowly across the sky, stars maintain their positions relative to one another. Orion keeps its shape. The Big Dipper stays recognizable. Constellations rise and set season after season with dependable regularity. To early civilizations, the stars looked eternal and unchanging. They became navigation markers, seasonal calendars, religious symbols, and storytelling tools. And to be fair, from a human perspective, stars barely change at all. A star can live for billions or trillions of years. Human beings tend to get excited when a building survives 3 centuries without becoming a coffee shop. Stellar evolution unfolds on timescales so enormous that even civilizations appear temporary by comparison. Because of that, no ancient observer could directly watch a star evolve from one type into another. The sky seemed static, permanent, immovable. But appearances in astronomy are often misleading. One of the earliest breakthroughs came from something deceptively simple: careful measurement of brightness. Ancient Greek astronomers, especially Hipparchus, began ranking stars according to apparent brightness. The brightest stars became first magnitude stars. Slightly dimmer ones became second magnitude, then third magnitude, and so on. It was an imperfect system, but it represented an important shift. Astronomers were no longer merely naming stars or connecting them into mythological figures. They were beginning to compare them quantitatively. Even so, they still lacked crucial information. Brightness alone tells you almost nothing about what a star truly is. A nearby dim star can appear brighter than an extremely luminous distant one. Without knowing stellar distances, astronomers had no reliable way to determine whether stars differed intrinsically or merely appeared different because of location. That problem persisted stubbornly for a very long time. Then telescopes arrived. When Galileo Galilei pointed a telescope toward the heavens in the early 17th century, the night sky suddenly became far more crowded. Regions that looked dark to the naked eye revealed countless faint stars. The Milky Way transformed from a cloudy band into an enormous collection of individual points of light. That alone was unsettling enough. The universe immediately became larger and more populated than anyone had imagined. Still, telescopes did not solve the deeper mystery of what stars physically were. Even through powerful instruments, most stars remained unresolved points. Planets showed disks. Jupiter revealed moons. Saturn displayed its rings. But stars stayed frustratingly tiny. Astronomers could magnify their brightness, not their surfaces. For a while, classification remained mostly descriptive. Stars were catalogued by position, brightness, and colour. Some observers noticed that reddish stars often appeared cooler in hue, while bluish stars looked sharper and more intense. But nobody yet understood why. The real revolution began in the 19th century with the development of spectroscopy. And spectroscopy is one of those scientific tools that sounds mildly technical until you realise it completely transformed humanity's understanding of the universe. The principle itself is straightforward. When light passes through a prism or diffraction grating, it separates into different wavelengths, producing a spectrum, like sunlight splitting into a rainbow. But astronomers noticed something strange inside stellar spectra. Dark lines interrupted the smooth bands of colour. At first, nobody understood what these lines meant. Then scientists discovered that chemical elements absorb specific wavelengths of light. Hydrogen absorbs certain colours, sodium absorbs others, calcium, iron, helium, oxygen. Each element leaves a unique pattern of spectral lines. In other words, light carried information. That realization changed astronomy forever. Suddenly, astronomers could analyze stars chemically without ever visiting them, which was fortunate because even the nearest star beyond the Sun is over 4 light-years away, and walking there would take an extremely unreasonable amount of time. Spectroscopy revealed something extraordinary almost immediately. The same elements found on Earth existed inside stars. The heavens were not composed of mystical celestial material. Stars contained ordinary matter obeying recognizable physical laws. Hydrogen dominated stellar spectra. Helium appeared too. Metals existed in smaller amounts. The universe suddenly looked unified rather than divided into earthly and heavenly realms. Astronomy became astrophysics, and once astronomers started examining stellar spectra systematically, they noticed patterns. Certain stars displayed strong hydrogen lines, others showed stronger helium signatures. Some revealed metallic absorption lines more prominently. Initially, this became slightly chaotic. During the late 19th century, astronomers at Harvard College Observatory began an enormous effort to classify stellar spectra. Thousands upon thousands of photographic plates needed analysis. Human beings had essentially created more astronomical data than existing classification systems could comfortably handle. This is where several remarkable women entered the history of astronomy, though for many years they received far less recognition than they deserved. One of the most important was Williamina Fleming, who helped organise early stellar classification systems. She worked among a group later nicknamed the Harvard Computers, women employed to analyse astronomical data manually. The term computer at the time referred to people, not machines. Imagine spending your entire workday examining photographic plates of stars, carefully identifying spectral lines by hand for thousands upon thousands of objects. Modern astronomers sometimes complain when software takes several minutes to process data. The Harvard computers accomplished enormous calculations using pencils, patience, and alarming levels of concentration. Fleming initially developed a classification system based largely on hydrogen line strength. Stars received categories labelled A through Q. It was useful, but not physically complete. Then Annie Jump Cannon refined the system dramatically, and this is where stellar classification begins taking the recognisable form still used today. Cannon realised that many spectral differences could be explained primarily by temperature. Hotter stars ionised atoms differently, altering spectral absorption lines. Cooler stars displayed entirely different patterns. She reorganised the categories into the famous sequence O, B, A, F, G, K, M. A wonderfully unintuitive ordering that generations of astronomy students have struggled to memorise ever since. Astronomers eventually invented mnemonic phrases to help remember the sequence, some polite, some less polite. Science occasionally pretends to be solemn, but give researchers enough time and they will absolutely start creating questionable memory aids. The sequence itself represents decreasing stellar surface temperature. O-type stars are the hottest, appearing blue or blue-white, with surface temperatures exceeding 30,000 Kelvin. M-type stars are the coolest major class, appearing reddish, often below 3,500 Kelvin. Our Sun belongs to class G, right in the middle. At first glance, this system might seem purely organisational, but it revealed something profound. Stellar colour directly corresponds to temperature through blackbody radiation physics. A hotter object emits more short-wavelength light, shifting toward blue. Cooler objects emit more long-wavelength light, shifting toward red. That principle explains why heated metal glows red first, then orange, then white, as temperature rises. Stars follow the same physics, just on scales involving terrifying amounts of energy. And once temperature became understood, astronomers realized stars were not random scattered objects. They formed families governed by physical laws. Hot blue stars tended to be massive and luminous. Cool red stars were usually smaller and dimmer. White stars occupied intermediate ranges. Spectra revealed ionization states, chemical composition, density, and motion. Stars suddenly became measurable physical systems. But another major breakthrough was still coming. In the early 20th century, astronomers began plotting stars according to luminosity and temperature. One of the resulting diagrams, developed independently by Einar Hertzsprung and Henry Norris Russell, became one of the most important tools in astrophysics, the Hertzsprung-Russell diagram, or HR diagram, because astronomers occasionally shorten things once they become tired of typing long surnames repeatedly. The HR diagram revealed an astonishing pattern. Stars did not distribute randomly. Most fell along a narrow band called the main sequence. Giant stars occupied one region, white dwarfs clustered elsewhere. For the first time, astronomers saw stellar evolution hiding inside observational data. This was revolutionary because it implied stars changed over time. That may sound obvious now, but at the time it represented a major conceptual shift. The sky was not static. Stars had life cycles. They formed, evolved, aged, and died, according to understandable physical processes. The HR diagram essentially became a map of stellar lives. A star's position on the diagram depended largely on mass. Massive stars appeared hot and luminous near the upper left. Small red dwarfs clustered toward the lower right. And once nuclear fusion became understood during the 20th century, the entire picture clicked together beautifully. Stars shine because fusion converts mass into energy. More massive stars compress their cores more strongly, raising temperatures and increasing fusion rates dramatically. That produces greater luminosity and hotter surface temperatures. The physics finally connected. Classification was no longer just descriptive bookkeeping, it became explanatory science. Astronomers could now understand why stars differed. Mass determined core pressure. Core pressure determined temperature. Temperature controlled fusion. Fusion controlled luminosity, colour, lifespan, and eventual fate. The classification system reflected underlying physics. And the deeper astronomers looked, the stranger stellar diversity became. Some stars varied in brightness rhythmically. Others existed in binary systems orbiting companions. Certain stars rotated extremely rapidly. Some possessed intense magnetic fields. Others lost mass through stellar winds so powerful they could strip away outer layers entirely. Variable stars became especially important because some types, like Cepheid variables, allowed astronomers to measure cosmic distances. Their pulsation periods correlated directly with intrinsic luminosity. That relationship helped reveal the true scale of the universe. Before then, astronomers debated whether spiral nebulae were nearby gas clouds or distant galaxies. Cepheid variables helped settle the argument. Galaxies lay enormously far away. The universe instantly became vastly larger. Again. Astronomy has a long history of humbling human assumptions about scale. Every time people become comfortable imagining the universe, new observations arrive to calmly inform us that reality is bigger, stranger, and operating under less intuitive rules than expected. Stellar classification kept expanding too. Subcategories emerged. Luminosity classes appeared. Roman numerals distinguished supergiants from giants and main sequence stars. Brown dwarfs required entirely new classifications beyond M-type stars, introducing L, T, and Y spectral classes. The universe, it turned out, was not content with a simple alphabet. Modern stellar classification now combines spectral type, luminosity class, temperature, metallicity, rotation, variability, magnetic properties, and more. A single stellar classification can encode enormous amounts of physical information. Take the Sun, classified as G2V. G means yellow-white surface temperature around 5,800 Kelvin. The 2 refines its exact position within the G category. V indicates main sequence luminosity class. Compact, precise, entirely based on measurable physics. And today, astronomers classify stars using technologies earlier generations could barely imagine. Space telescopes analyze spectra across ultraviolet, visible, infrared, and X-ray wavelengths. Computers process millions of stars automatically. Large surveys mapped stellar populations across entire galaxies. The European Space Agency's Gaia mission alone has measured positions, motions, and properties for over 1 billion stars. 1 billion. That number is difficult to emotionally process. Human civilization once relied on small groups of observers staring upward with naked eyes. Now, robotic observatories continuously measure stellar temperatures, motions, distances, and compositions across enormous regions of the Milky Way. And despite all this progress, classification still serves the same basic purpose it always has. Humans trying to organize patterns inside overwhelming complexity. That instinct appears almost universal in science. First observe, then compare, then categorize, eventually understand. Of course, nature rarely respects neat categories completely. Some stars refuse to behave conveniently. Others transition between states. Binary interactions distort evolution dramatically. Exotic objects blur distinctions between star, planet, and stellar remnant. The universe enjoys exceptions. Still, classification remains essential because it reveals order hiding beneath apparent chaos. Stellar types are not arbitrary labels. They reflect underlying physical laws operating consistently across space, and perhaps most remarkably, astronomers achieved all of this without physically visiting a single star. Everything came from light. Tiny streams of photons crossing impossible distances through space, carrying encoded information about temperature, motion, chemistry, density, gravity, and magnetic fields. That realization remains one of humanity's greatest intellectual achievements. We learned how to decode starlight. And once astronomers understood how to classify stars properly, the next question became unavoidable. If stars occupy different categories because of their physical properties, where do those differences actually begin? Out between the stars, far beyond the bright regions where fully formed suns shine steadily for billions of years, enormous clouds of gas drift quietly through the galaxy. Most of the time, these clouds remain cold, dark, and uneventful. If you pass through one, you might barely notice it. Even the densest star-forming nebulae are vastly emptier than the best vacuums humans can produce on Earth. Space is extraordinarily sparse. And yet, despite that emptiness, these giant molecular clouds contain enough material to create entire generations of stars. This is where stellar life begins, not with fire, not with light, not even with fusion. It begins with gravity slowly gathering cold hydrogen gas together over immense stretches of time. That process sounds simple, but in reality it involves an intricate balance between pressure, temperature, turbulence, magnetic fields, angular momentum, and radiation. Star formation is one of those areas of physics where several different forces all attempt to complicate one another simultaneously. Gravity, however, is extremely patient. A molecular cloud may drift through the galaxy for millions of years before anything dramatic happens. These clouds are composed mostly of hydrogen molecules, along with helium and trace amounts of heavier elements left behind by earlier generations of stars. Temperatures often sit around just 10 to 20 Kelvin, only slightly above absolute zero. Cold temperatures matter enormously here. Hot gas expands because particles move rapidly and resist compression. Cold gas moves more slowly, allowing gravity a better chance to pull material inward. In a sense, star formation requires the universe to calm down first. Eventually something disturbs part of the cloud. Sometimes nearby supernova explosions send shockwaves through the gas. Sometimes galactic collisions compress material. Sometimes gravity itself slowly amplifies tiny density fluctuations already present inside the cloud. A slightly denser region attracts slightly more material, becoming denser still. This process is runaway collapse. Once gravity gains enough advantage, the region begins contracting inward, and at that moment the future star technically exists, though nobody would recognize it yet. Astronomers call these collapsing regions dense cores. Their masses vary enormously. Some may eventually form small red dwarfs. Others may create massive blue giants or even clusters containing thousands of stars. One particularly important concept here is the gene's instability, named after James genes. Genes calculated the conditions under which gravity overcomes internal gas pressure and triggers collapse. The idea is surprisingly intuitive. If a cloud contains too little mass, internal pressure prevents contraction. But once enough matter accumulates within a given region, gravity wins. Collapse becomes unavoidable. It's essentially the universe's version of a tipping point. Below the threshold, gas remains diffuse. Above it, the cloud starts falling inward under its own weight. And once collapse begins, something fascinating happens. Gravitational potential energy converts into heat. As particles fall inward, they accelerate. Collisions become more frequent. Temperatures rise. The cloud starts warming from the inside out. At first, the collapsing core remains invisible in visible light because surrounding dust absorbs radiation. But infrared telescopes reveal glowing warm regions hidden inside dark nebulae. Modern astronomy has allowed humans to peer directly into stellar nurseries where stars are actively forming, and honestly some of them look astonishingly chaotic. Popular illustrations often depict star formation as smooth and elegant, but actual stellar nurseries resemble turbulent storms of gas, dust, jets, radiation, and magnetic interactions unfolding across enormous distances. Gravity tries to compress material inward, while angular momentum resists collapse. Magnetic fields thread through the gas. Nearby newborn stars blast surrounding regions with ultraviolet radiation. It is not a calm environment. One major problem during collapse involves angular momentum. Even very slight rotation becomes important as material contracts. Think about an ice skater pulling their arms inward and spinning faster. Conservation of angular momentum forces collapsing clouds to rotate increasingly rapidly as they shrink. Without some way to shed angular momentum, stars could never fully form. The collapsing gas would spin too fast and stabilize before reaching stellar densities. Nature solves this through accretion disks. Instead of collapsing directly into a sphere immediately, infalling material flattens into a rotating disk around the growing central object. Gas spirals inward gradually while angular momentum transfers outward through turbulence, magnetic interactions, and disk dynamics. These disks are extraordinarily important because they also become the birthplaces of planets later on. In other words, the same structure helping stars form often eventually produces solar systems. Right now, somewhere in the Milky Way, countless disks of gas and dust are circling young protostars while planets quietly begin assembling grain by grain, and while all this is happening, the central object continues heating up. At this stage, astronomers call it a protostar. A protostar is not yet a true star because nuclear fusion has not fully ignited in its core. Its energy comes primarily from gravitational contraction. As material falls inward, compression heats the interior further and further. Temperatures climb into the thousands, then hundreds of thousands, then eventually millions of degrees. Meanwhile, the surrounding environment becomes increasingly violent. Young protostars often produce bipolar jets, narrow streams of material blasted outward from the poles at enormous speeds. Magnetic fields interacting with rotating accretion disks help channel plasma into these spectacular outflows. The result can look almost absurdly dramatic. A forming star quietly gathering gas while simultaneously firing enormous plasma jets across interstellar space. Astronomy has a habit of mixing slow patience with sudden violence. These jets actually help star formation continue by carrying away excess angular momentum. Without them, material would struggle to spiral inward efficiently, and as the protostar grows hotter, radiation pressure begins pushing outward against surrounding gas. Massive protostars especially become difficult to build because their intense radiation starts disrupting infalling material before formation finishes. There is effectively a race between gravity pulling matter inward and radiation pushing it away. For small stars like red dwarfs, gravity usually proceeds relatively calmly. Massive stars, however, become unstable almost immediately. Some begin nuclear fusion while still accreting surrounding gas, and throughout all this, timescales vary enormously depending on mass. Small red dwarf protostars may take hundreds of millions of years to settle fully onto the main sequence. Massive stars can form astonishingly quickly by comparison, sometimes in only a few 100,000 years. Again, mass controls nearly everything. Larger masses produce stronger gravity. Stronger gravity drives faster collapse. Faster collapse raises core temperatures more rapidly. Eventually, if enough mass accumulates, the core temperature reaches roughly 10 million Kelvin. And this is the critical threshold, because at those temperatures hydrogen nuclei begin overcoming their mutual electrostatic repulsion. Under ordinary conditions, positively charged protons repel one another strongly. Fusion requires forcing them close enough together for the strong nuclear force to bind them. That is extraordinarily difficult. The Sun's core accomplishes it only because immense pressure and temperature create vast numbers of high-energy collisions every second. Inside a protostar approaching stellar ignition, conditions finally become extreme enough for sustained hydrogen fusion to begin, and once that happens, the object becomes a true star. The transition is one of the most important moments in astrophysics. For millions of years, gravity dominated the evolution of the protostar, but fusion introduces a new energy source powerful enough to counterbalance collapse. Hydrostatic equilibrium emerges. Outward thermal pressure from fusion balances inward gravitational compression. A stable star is born. Technically, this stage is called reaching the main sequence. The star now spends the majority of its life steadily fusing hydrogen into helium in its core. What happens afterward depends primarily on mass. A small red dwarf settles into a slow-burning existence lasting trillions of years. A sun-like star begins a more moderate life cycle lasting billions. Massive blue stars ignite with extraordinary violence and race rapidly toward future instability. But before any of those futures unfold, all stars must first survive formation, and that process can fail. Not every collapsing cloud gathers enough mass to ignite hydrogen fusion. Some objects stall before reaching the critical threshold of roughly 0.08 solar masses. These become brown dwarfs. Brown dwarfs occupy a strange middle ground between planets and stars. They're too massive to classify comfortably as planets, yet not massive enough to sustain ordinary hydrogen fusion. Some briefly fuse deuterium or lithium during early stages, but they never become true stable stars. For a long time, astronomers suspected such objects should exist, but detecting them proved difficult because brown dwarfs emit very little visible light. They cool steadily over time, glowing mostly in infrared wavelengths. It wasn't until the 1990s that convincing brown dwarf discoveries finally arrived. And once astronomers found them, they appeared everywhere. The universe, it turns out, produces many almost stars. That outcome highlights something important about stellar formation. Gravity alone does not guarantee success. Conditions must align properly. Enough mass must accumulate before radiation, turbulence, or external disturbances interrupt collapse. In some star-forming regions, multiple protostars form together inside the same cloud. Binary and multiple star systems are extremely common. In fact, many stars do not live alone at all. That has major consequences later. Companion stars can exchange matter, distort one another gravitationally, trigger novae, alter supernova behavior, and dramatically reshape stellar evolution. Some stars even get ejected entirely from their birth clusters through gravitational interactions, becoming runaway stars racing through the galaxy at enormous speeds. Stellar nurseries are crowded places. Observations of regions like Orion Nebula reveal thousands of young stars forming simultaneously inside giant molecular clouds. Many remain wrapped in disks. Some are still heavily embedded inside dusty cocoons. Others already emit strong stellar winds, clearing away surrounding gas. And importantly, those surrounding environments affect planet formation too. Radiation from nearby massive stars can evaporate protoplanetary disks around smaller stars. Supernova explosions enrich surrounding gas with heavier elements. Shockwaves trigger new rounds of collapse nearby. Star formation is not isolated. It propagates. One generation of stars creates conditions influencing the next generation. Massive stars especially play outsized roles because they evolve quickly and die violently, returning enriched material to interstellar space. Without earlier generations of stars, rocky planets and life itself would not exist. The early universe contained mostly hydrogen and helium. Heavier elements formed later inside stars and during supernova explosions. Every carbon atom in your body once passed through stellar interiors. That statement remains quietly extraordinary. Human beings often think of stars as distant scenery, but chemically speaking, we are direct products of stellar evolution. The atoms composing Earth, oceans, atmosphere and living organisms were assembled through nuclear processes inside long-dead stars billions of years ago. Protostars represent the beginning of that ongoing cycle. Cold gas collapses, fusion ignites, stars shine, heavy elements form, stars die, material returns to space, new stars emerge, again and again across cosmic history. Even now, the Milky Way forms new stars continuously, though at a relatively moderate pace compared to intensely active galaxies. Somewhere tonight, hidden within dark molecular clouds, gravity is slowly gathering matter together toward future ignition. Some of those protostars may eventually host planets. Some planets may develop oceans. Somewhere, billions of years from now, intelligent life could look upward at entirely different skies while studying stellar physics just as we do now. And the laws governing those stars will be exactly the same. Gravity compressing matter inward, pressure resisting collapse, fusion igniting once temperatures rise high enough. The remarkable thing about protostars is not merely that they create stars, it is that such complexity emerges naturally from relatively simple physical rules, applied consistently over enormous spans of time. No external guidance is required. The universe simply allows gravity to operate patiently enough, and eventually stars appear. Some small, some enormous, some stable, some catastrophically unstable. If you stepped outside tonight and looked up at the sky, most of the stars surrounding you would probably not be visible at all. That sounds slightly unfair considering how many of them are out there, but red dwarfs are not particularly concerned with attracting attention. They are small, dim, cool compared to stars like the Sun, and remarkably efficient at conserving fuel. Even though they are by far the most common type of star in the Milky Way, none are bright enough to stand out prominently in Earth's night sky with the naked eye. And yet, statistically speaking, red dwarfs dominate the galaxy. Some estimates suggest that around 70% to 80% of all stars in the Milky Way are red dwarfs. If you randomly selected a star from our galactic neighbourhood, chances are overwhelming that you would end up with one of these faint little objects quietly burning hydrogen somewhere in the darkness. Astronomy often behaves this way. The universe's most common things are rarely the most dramatic. Massive blue giants may capture attention because they blaze with extraordinary brightness, but they are cosmically rare. Red dwarfs, meanwhile, sit quietly in enormous numbers, steadily continuing their slow nuclear reactions while larger stars explode themselves out of existence. In a sense, red dwarfs are the universe's long-term planners. Physically, red dwarfs occupy the lower end of stellar masses. They typically range from about 0.08 to 0.6 solar masses. Below roughly 0.08 solar masses, hydrogen fusion cannot sustain itself, and the object becomes a brown dwarf instead. Above the red dwarf range, stars become hotter and more luminous. Main sequence stars like orange dwarfs, yellow dwarfs, and eventually blue stars. That lower mass changes everything. Because gravity compresses red dwarf cores less intensely than the cores of larger stars, their internal temperatures remain comparatively modest. A typical red dwarf may have surface temperatures between about 2,500 and 4,000 Kelvin, giving them their reddish appearance. By comparison, the Sun's surface temperature sits around 5,800 Kelvin. That difference may not sound enormous at first, but stellar radiation changes dramatically with temperature. Hotter stars emit much more energy, especially at shorter wavelengths. Blue stars can outshine red dwarfs by factors of thousands or even millions. A red dwarf is not merely a slightly smaller sun, it is an entirely different style of stellar existence. The physics governing these stars makes them astonishingly economical with energy. Inside a red dwarf's core, hydrogen fusion proceeds primarily through the proton-proton chain, the same general mechanism powering the Sun. Positively charged hydrogen nuclei collide under immense pressure and temperature, eventually combining into helium while releasing energy. The process still relies on Einstein's equation, E equals mc square. Mass converts into energy. Radiation pushes outward. Gravity pulls inward. Hydrostatic equilibrium stabilizes the star, but because red dwarfs possess lower core temperatures, fusion occurs much more slowly. And this is where their extraordinary longevity begins. The Sun converts roughly 600 million tons of hydrogen into helium every second. That number sounds absurd because it is absurd. Stellar energy production operates on scales the human brain does not naturally process comfortably. Yet compared to larger stars, even the Sun is relatively restrained. Massive blue stars burn through fuel with astonishing recklessness, consuming hydrogen at enormous rates to maintain their tremendous luminosities. Red dwarfs do the opposite. They sip fuel carefully. A small red dwarf may emit less than 1,000th the luminosity of the Sun. Some are so dim that even from relatively nearby distances they remain invisible without telescopes. But low luminosity comes with a massive advantage: efficiency. Massive stars waste energy rapidly because their intense gravity forces extremely high core temperatures. Red dwarfs avoid this problem entirely. Their cores remain cool enough to support slow, controlled fusion rates. And there's another important detail. The Sun and larger stars are not fully convective. Their cores perform fusion while outer layers behave differently. Helium ash gradually accumulates in the center, limiting how much hydrogen becomes available for future fusion. Red dwarfs, however, are often fully convective. This changes their internal physics dramatically. Convection occurs when hot material rises while cooler material sinks, transferring energy through bulk motion. like boiling water circulating inside a pot. In many red dwarfs, convection extends throughout nearly the entire star. That means hydrogen from outer regions continuously mixes inward, while helium from the core mixes outward. The result is extraordinary fuel efficiency. Instead of burning only a fraction of available hydrogen, fully convective red dwarfs can utilize much larger percentages of their total mass for fusion. Combined with their already slow fusion rates, this gives them lifespans almost difficult to comprehend. The smallest red dwarfs may survive for trillions of years, not billions, trillions. And this creates one of the strangest facts in stellar astrophysics. The universe is not old enough for any red dwarf to have died naturally yet. None. The cosmos itself is approximately 13.8 billion years old, but many red dwarfs are expected to survive hundreds of billions or even trillions of years into the future. Every red dwarf ever formed still exists. In a very real sense, red dwarfs are eternal relative to current cosmic history. This also means astronomers cannot directly observe the full life cycle of a red dwarf because none have yet completed one naturally. Scientists must rely on theoretical models to predict their future evolution. According to current understanding, red dwarfs gradually become hotter and brighter over immense timescales as helium accumulates. Eventually, after exhausting hydrogen, the smallest may transition into hypothetical blue dwarf stages before cooling into white dwarfs. Interestingly, the universe itself may not even remain hospitable long enough for many of these later stages to fully unfold. Red dwarfs live on timescales approaching the far future evolution of galaxies themselves. They are cosmic endurance champions. Of course, longevity comes with trade-offs. Red dwarfs are not always calm and friendly environments, especially when young. Many exhibit intense magnetic activity. Because they rotate relatively rapidly and possess deep convective interiors, red dwarfs can generate powerful magnetic fields through dynamo processes. Those magnetic fields often produce enormous stellar flares. Some red dwarf flares are genuinely extreme. A single flare can release vast amounts of ultraviolet radiation, X-rays, and charged particles into surrounding space. Planets orbiting nearby may experience repeated radiation bombardment capable of stripping atmospheres or disrupting surface conditions, and because red dwarfs are dim, their habitable zones lie very close to the star. This creates an awkward situation. A planet must orbit nearby to receive enough warmth for liquid water, but proximity also exposes it to stellar flares, magnetic storms, and tidal effects. Many potentially habitable red dwarf planets may become tidally locked as well. Tidal locking occurs when one side of a planet permanently faces its star, while the other side remains in perpetual darkness. Earth's moon is tidally locked to Earth, always showing us the same hemisphere. For planets around red dwarfs, tidal locking can happen relatively quickly because orbital distances are so small. At first glance, that sounds disastrous. One side baking endlessly under starlight while the other freezes in darkness. But atmospheric circulation could complicate matters significantly. Thick atmospheres and oceans might redistribute heat effectively enough to support stable climates between extremes. Astronomers continue debating these possibilities actively because red dwarf systems have become major targets in the search for extraterrestrial life. And there are many such systems nearby. The nearest star to the Sun, Proxima Centauri, is a red dwarf. It hosts at least one known exoplanet within its habitable zone. Likewise, TRAPPIST-1 contains 7 Earth-sized planets, several orbiting within temperature ranges where liquid water could potentially exist. The discovery of systems like these transformed discussions about habitability across the galaxy. Before exoplanet discoveries accelerated during recent decades, many scientists focused primarily on sun-like stars as likely hosts for life. But because red dwarfs are so abundant, even modest probabilities of habitability could imply enormous numbers of potentially life-supporting worlds. the galaxy may contain countless rocky planets orbiting dim red suns. Of course, potentially habitable and actually inhabited are very different things. Red dwarf environments pose real challenges. Young red dwarfs especially can remain magnetically active for billions of years. Strong flares may repeatedly sterilize planetary surfaces or erode atmospheres, unless magnetic fields or thick atmospheres provide protection. Then again, life on Earth has demonstrated remarkable resilience under difficult conditions. Organisms survive deep underground near hydrothermal vents, inside acidic lakes, beneath Antarctic ice, and in high radiation environments. Biology is annoyingly adaptable. It is entirely possible that alien ecosystems around red dwarfs, if they exist, evolved under conditions very different from Earth's relatively stable sunlight. Imagine civilizations living beneath the reddish glow of a dim star that barely changes for trillions of years. Their skies would look different. Their seasons might behave differently. Their understanding of stellar evolution would differ dramatically from ours, because their star would appear effectively eternal. A red dwarf civilization, given enough time, might watch larger neighbouring stars live entire lifetimes while their own sun barely changes at all. That thought alone highlights how profoundly stellar mass shapes cosmic experience. For humans, the sun seems permanent, because our civilization spans tiny fractions of stellar lifetimes. But around massive blue stars, civilizations might never have enough time to evolve before the star itself dies catastrophically. Around red dwarfs, meanwhile, time stretches almost unimaginably far into the future. And in that far future, red dwarfs may become the dominant surviving stars of the universe. Massive stars die quickly in supernova explosions. Sun-like stars eventually shed outer layers and become white dwarfs. But the countless red dwarfs scattered throughout galaxies will continue burning quietly long after brighter stars vanish. Future galaxies may become dimmer, redder places illuminated mostly by these faint survivors. There is something oddly fitting about that. The smallest stars ultimately outlasting the giants. Physics sometimes rewards patience more than intensity. Observationally, red dwarfs remained difficult to study for much of astronomical history because of their faintness. Even nearby examples can be challenging targets compared to brighter stars visible across vast distances. Modern infrared telescopes improved matters enormously. Red dwarfs emit much of their radiation at longer wavelengths, making infrared observations especially useful. And once astronomers began surveying them systematically, another surprise emerged. Many red dwarfs host planets. Planet formation appears remarkably efficient around these stars. Small rocky worlds seem especially common. Some systems contain tightly packed planetary arrangements unlike anything in our solar system. Again, the universe refused to limit itself to familiar patterns. This has major implications for galactic demographics. If red dwarfs dominate stellar populations and frequently host rocky planets, then statistically, much of the galaxy's planetary real estate likely exists around these dim stars rather than around sun-like stars. Human beings evolved around a G-type yellow dwarf, but cosmically speaking, that may not represent the most common environment at all. In fact, the Sun is somewhat unusual compared to the galaxy's dominant stellar population. Astronomy repeatedly teaches variations of the same lesson. Humans tend to assume familiar things are typical. The universe calmly disagrees. Even so, red dwarfs are not merely smaller versions of larger stars. Their fully convective interiors, prolonged magnetic activity, extreme lifespans, and unique planetary environments make them fundamentally distinct stellar systems, and because they survive so long, they may ultimately witness phases of cosmic history no current civilization can truly imagine. Trillions of years from now, after many galaxies evolve, after star formation slows dramatically, after luminous massive stars disappear entirely, the red dwarfs may still remain, quietly fusing hydrogen, steadily conserving fuel, continuing onward while brighter stars have already burned themselves away. Compared to the tiny red dwarfs quietly stretching their fuel across trillions of years, yellow and orange dwarf stars occupy a very different middle ground in stellar physics. They are hotter, brighter, more massive and significantly less patient, but they are also remarkably stable. Stable enough in some cases to support planetary systems for billions of years without catastrophic changes in luminosity or violent magnetic activity overwhelming nearby worlds. This balance is extremely important, because once astronomers began studying exoplanets seriously, it became increasingly clear that stable stars provide something valuable: time. Complex chemistry requires time. Planetary cooling requires time. Biological evolution, at least based on the only example humans currently know about, requires enormous stretches of environmental stability. A star that erupts violently every few days or exhausts its fuel too quickly creates difficult conditions for long-term planetary development. Yellow and orange dwarfs, particularly those on the main sequence, solve that problem rather elegantly. And the reason they remain stable for such long periods comes down to one of the most important concepts in astrophysics: hydrostatic equilibrium. That phrase sounds intimidating at first, but the underlying idea is actually very straightforward. Inside every stable star, two enormous forces continuously oppose one another. Gravity pulls inward, pressure pushes outward. Gravity constantly attempts to compress the star further. Every layer of stellar material feels the weight of material above it pressing inward toward the core. If gravity acted alone, stars would collapse rapidly under their own mass. But fusion inside the core changes everything. Nuclear reactions release enormous amounts of energy. That energy heats stellar plasma to extraordinary temperatures, generating pressure capable of resisting gravitational collapse. Radiation pressure and thermal gas pressure push outward while gravity pulls inward. When these forces balance successfully, the star stabilizes. Astronomers call this balance hydrostatic equilibrium. A star is essentially a gigantic, self-regulating physics engine suspended between collapse and explosion. That balance remains remarkably precise. If fusion slows slightly, gravity compresses the core further. Compression raises temperature and pressure, increasing fusion rates again. If fusion becomes too energetic, the star expands slightly, cooling the core and reducing reaction rates. Stars automatically correct small instabilities through ordinary physical laws. The result is astonishingly long-lived stability. Yellow and orange dwarfs exist in a mass range where this equilibrium becomes especially reliable. They are massive enough to sustain steady hydrogen fusion efficiently, but not so massive that fusion rates spiral uncontrollably upward like they do in blue giant stars. This creates some of the most stable long-term stellar environments in the galaxy. Our own Sun is the most famous example. The Sun belongs to spectral class G2V. The G refers to its surface temperature and spectral properties. The 2 refines its position within the G class. The V indicates that it is a main sequence star undergoing stable hydrogen fusion. At roughly 5,800 Kelvin on the surface, the Sun emits most strongly invisible wavelengths, producing the familiar yellow-white light illuminating Earth. Interestingly, from space the Sun actually appears nearly white rather than strongly yellow. Earth's atmosphere scatters shorter blue wavelengths, subtly altering our perception from the surface. Astronomy occasionally reminds us that even the colour of our own star depends partly on atmospheric physics. Inside the Sun's core, temperatures reach roughly 15 million Kelvin. At those conditions, hydrogen nuclei collide with sufficient energy for sustained proton-proton fusion reactions. The dominant chain begins with ordinary hydrogen nuclei, protons, combining through a series of reactions eventually producing helium. Mass converts into energy, according to Einstein's famous relation. Every second, the Sun converts roughly 4 million tons of mass directly into energy. And despite those extraordinary numbers, the Sun remains incredibly stable because the total mass involved is tiny compared to the Sun's full mass of approximately 2 × 10⁻30 kilograms. At current fusion rates, the Sun possesses enough hydrogen fuel to continue stable main sequence burning for about another 5 billion years. That long lifespan emerges directly from moderate stellar mass. If the Sun were significantly more massive, core temperatures would rise sharply, increasing fusion rates enormously. Luminosity scales very steeply with stellar mass. Even modest increases in mass produce disproportionately large increases in energy output. A star twice the Sun's mass may shine many times brighter while exhausting fuel far more rapidly. This relationship creates one of the great paradoxes of stellar evolution. Larger stars contain more fuel yet live shorter lives. Physics can be slightly rude that way. Orange dwarfs push stability even further than the Sun in some cases. These stars, typically spectral class K, are somewhat smaller and cooler than yellow dwarfs, but still sustain long-term stable fusion. One excellent example is Alpha Centauri b. Alpha Centauri b forms part of the nearest stellar system to Earth beyond the Sun. Slightly smaller and cooler than the Sun, it emits a softer orange-tinted light and burns fuel more slowly. Many astronomers consider K-type orange dwarfs especially interesting for potential habitability studies. They combine several advantages. Unlike many red dwarfs, orange dwarfs tend to exhibit lower long-term flare activity. Their habitable zones lie farther out, reducing tidal locking issues for orbiting planets. Yet they also live longer than Sun-like stars, potentially providing stable planetary environments for tens of billions of years. Some researchers informally call K-type stars Goldilocks stars because they may represent especially favourable balances between longevity and stability. Not too violent, not too short-lived, not too dim, just stable enough for very long stretches of planetary evolution. Another well-known orange dwarf is Epsilon Indi. Located relatively nearby on cosmic scales, Epsilon Indi has attracted interest partly because of its surrounding system, including brown dwarf companions. Observations of systems like this help astronomers understand how stellar mass influences planetary and substellar formation processes. Then there is Tau Ceti, one of the nearest Sun-like stars and a frequent target in discussions about nearby potentially habitable planetary systems. Tau Ceti resembles the Sun in several ways, but contains somewhat lower metallicity, meaning it formed from material with fewer heavy elements compared to younger stars like the Sun. Metallicity matters greatly in astrophysics. Early generations of stars formed primarily from hydrogen and helium, because heavier elements had not yet been produced extensively through stellar nucleosynthesis. Later stellar generations inherited increasing amounts of carbon, oxygen, iron, silicon, and other elements recycled through supernova explosions and stellar winds. The Sun itself belongs to a relatively metal-rich generation of stars. Without those heavier elements, rocky planets like Earth would not form. This means yellow and orange dwarfs not only provide stable energy sources, but also often emerge in eras of cosmic history where planet formation becomes increasingly complex. That connection between stellar evolution and planetary chemistry is one of the most remarkable aspects of astrophysics. Stars create the ingredients for future planets, which later orbit future stars formed from enriched material produced by earlier generations. Cosmic recycling on truly unreasonable scales. A fourth important example is 61 Virginis. 61 Virginis hosts multiple known exoplanets and represents another relatively stable Sun-like system studied extensively in exoplanet surveys. As astronomers discovered more planetary systems around yellow and orange dwarfs, it became increasingly obvious that planetary formation is not unusual at all. The Milky Way appears filled with planets. For most of human history, the solar system stood alone simply because our instruments lacked sufficient sensitivity. Once detection methods improved, planets began appearing everywhere. Many orbit stable main-sequence stars very similar to the Sun. Hydrostatic equilibrium remains central to understanding why these stars endure so reliably. Inside yellow and orange dwarfs, gravity and pressure maintain balance over enormous spans of time. The star neither collapses inward nor explodes outward because energy generation naturally adjusts to changing conditions. This self-regulation depends strongly on core temperature sensitivity. Fusion rates increase dramatically with temperature. A small increase in core compression raises fusion rates significantly, producing more outward pressure. The system stabilizes dynamically. In effect, stars behave somewhat like thermostats controlled entirely by nuclear physics and gravity, no external management required. And importantly, these stars spend the overwhelming majority of their lives on the main sequence. The main sequence is not merely a classification label. It represents the longest and most stable phase of stellar existence. During this period, hydrogen fusion in the core provides steady energy output, while hydrostatic equilibrium maintains structural stability. Eventually, however, hydrogen in the core gradually depletes. Helium accumulates. Fusion conditions begin changing, but that future lies billions of years ahead for stars like the Sun. Right now, the Sun remains approximately halfway through its stable hydrogen-burning lifetime. And during that stable period, something extraordinary happened on at least one small rocky planet orbiting it. Chemistry became biology. Biology became intelligence. Intelligence began studying stars. There is something deeply strange about that chain of events. Hydrogen formed shortly after the Big Bang. Gravity gathered gas into stars. Stars fused heavier elements. Supernovae distributed those elements into space. Planets formed. Molecules assembled. Life evolved. Eventually, collections of atoms produced inside ancient stars began constructing telescopes to study stellar evolution itself. The universe became self-observing through physics and time. And all of that depended on stellar stability lasting long enough for complexity to emerge gradually. A star too massive might explode before intelligent life evolves. A star too unstable may bombard planets with sterilizing radiation. A star too small and dim may create entirely different environmental constraints. Yellow and orange dwarfs occupy a remarkably favorable middle region in parameter space. Not perfectly, of course. Even the Sun changes over time. Its luminosity slowly increases as helium accumulates in the core. Billions of years from now, Earth may become uninhabitable long before the Sun itself dies. Stellar stability is relative, not eternal. Still, compared to massive stars, yellow and orange dwarfs are astonishingly dependable. The Sun's luminosity varies only slightly over ordinary human timescales. Solar cycles produce fluctuations in magnetic activity, sunspots, and solar flares, but the star remains broadly stable. That consistency allowed Earth's climate and biosphere to persist long enough for complex ecosystems to evolve. And from a physics perspective, all of this emerges naturally from mass. Again and again in stellar astronomy, mass controls fate. Slightly less mass produces cooler orange dwarfs with longer lifespans. Slightly more mass produces hotter stars with shorter lives. The balance between gravity and fusion shifts accordingly. Stars are not designed individually. The universe simply applies the same physical laws repeatedly under slightly different initial conditions. One cloud forms a red dwarf, another forms a yellow dwarf, another forms a blue giant destined for violent collapse. The outcomes differ enormously, but the underlying equations remain the same. And although yellow and orange dwarfs feel relatively calm compared to more extreme stars, their interiors still operate under astonishing conditions. The Sun's core pressure exceeds hundreds of billions of atmospheres. Plasma densities, radiation transport, magnetic fields, and nuclear reaction chains all interact continuously within regions hidden permanently beneath the visible surface. Even ordinary stars are profoundly extreme places. We simply become accustomed to them because one happens to sit at the centre of our solar system. Somewhere in the Milky Way tonight, there are stars shining with such intensity that if one replaced the Sun, Earth's surface would become uninhabitable almost immediately. Not warmer, not slightly uncomfortable, completely sterilised. Oceans would evaporate. Atmospheric chemistry would change violently. Radiation levels would surge. The familiar balance supporting life here would vanish very quickly under the overwhelming energy output of a truly massive blue star. And yet, despite their terrifying power, blue stars are relatively rare. That rarity makes sense once you understand how they work. Massive stars consume fuel at astonishing rates. They live briefly, die violently, and spend their entire existence balancing on the edge of instability. Compared to calm, long-lived red dwarfs or stable yellow stars like the Sun, blue stars behave more like enormous thermonuclear emergencies temporarily held together by gravity. From a physics perspective, they are extraordinary objects. Blue stars generally belong to the hottest spectral classes, primarily O-type and B-type stars. Surface temperatures range from roughly 10,000 Kelvin for some B stars to over 40,000 Kelvin for the hottest O stars. At those temperatures, stellar radiation shifts strongly toward shorter wavelengths. That is why these stars appear blue or blue-white. The relationship between temperature and emitted radiation follows blackbody physics. Hotter objects radiate more total energy and emit proportionally more short-wavelength light. A simplified version of Wien's law describes this relationship. Lambda max equals B divided by T. As temperature increases, peak emission wavelength decreases. Cool stars glow redder, hot stars shift toward blue. And blue stars are extremely hot. The underlying reason comes back once again to mass. Massive stars possess enormously stronger gravity than smaller stars. Gravity compresses their cores more intensely, raising pressure and temperature dramatically. Those higher core temperatures accelerate nuclear fusion at astonishing rates. This relationship is not linear. A star only several times more massive than the Sun can become tens of thousands, or even millions of times more luminous. That enormous increase in luminosity happens because fusion rates depend extremely sensitively on temperature. In stars like the Sun, hydrogen fusion primarily occurs through the proton-proton chain. But inside massive blue stars, core temperatures become high enough for a different mechanism to dominate, the CNO cycle. The carbon-nitrogen-oxygen cycle uses heavier elements as catalysts during hydrogen fusion. The reaction still converts hydrogen into helium. But the intermediate steps involve carbon, nitrogen, and oxygen nuclei participating in complex reaction chains. And critically, the CNO cycle becomes enormously temperature sensitive. A modest rise in core temperature can produce huge increases in energy generation. That creates a feedback loop. Massive stars develop hotter cores. Hotter cores accelerate fusion. Faster fusion increases luminosity enormously. Increased luminosity raises internal radiation pressure. Blue stars become incredibly bright because their cores are operating under much more extreme conditions than smaller stars. One famous example is Rigel. Rigel appears as one of the brightest stars in Earth's night sky. Despite lying hundreds of light years away, it radiates tens of thousands of times more energy than the Sun. If Rigel replaced the Sun, the entire appearance of the sky would change dramatically. Earth's daytime brightness would become overwhelming, and ultraviolet radiation levels alone would pose severe problems for life. Another extraordinary example is Spica. Spica actually consists of two massive stars orbiting closely together. Their intense radiation and rapid rotation distort their shapes and influence each other gravitationally. Massive stars often exist in binary or multiple systems because they commonly form inside dense stellar nurseries, where gravitational interactions occur frequently. Then there is Zeta Puppis, one of the hottest and most luminous stars visible from Earth. Zeta Puppis emits immense stellar winds, streams of charged particles flowing outward at enormous velocities. These winds carry away significant mass over time. That mass loss becomes critically important in massive star evolution. Blue stars are so luminous that their own radiation pushes material outward continuously. Photons carry momentum, and in massive stars the outward radiation pressure becomes strong enough to drive substantial stellar winds. In some cases, stars lose enormous amounts of material throughout their lifetimes. A fourth remarkable example is Delta Orionis, another hot blue stellar system containing massive stars interacting gravitationally. Observations of systems like these help astronomers understand how massive stars evolve under complex conditions involving tidal interactions, rotation, magnetic fields, and mass exchange, and blue stars evolve quickly, extremely quickly by stellar standards. This is one of the most counterintuitive aspects of astrophysics. A blue star may contain vastly more hydrogen than the Sun, yet it exhausts fuel far sooner because fusion rates increase disproportionately with mass. The Sun is expected to remain on the main sequence for roughly 10 billion years. Some massive O-type stars survive only a few million years. Cosmically speaking, that is almost nothing. Human civilization has existed for only tiny fractions of even those short stellar lifetimes, but compared to smaller stars, blue stars live recklessly fast. It is like comparing a slowly burning candle to an industrial furnace consuming fuel at catastrophic rates. And because these stars evolve so rapidly, they strongly influence their surrounding environments. Massive blue stars flood nearby space with ultraviolet radiation capable of ionizing surrounding hydrogen gas. Entire glowing nebulae exist because blue stars energize nearby material. The Orion Nebula, for example, glows partly because hot young stars illuminate and ionize surrounding gas. Blue stars also shape galactic evolution through their stellar winds and eventual deaths. Their radiation compresses nearby molecular clouds, potentially triggering new rounds of star formation. Their winds carve enormous cavities into interstellar space. And when they die, they explode as supernovae, distributing heavy elements across galaxies. Without massive stars, the universe would evolve chemically much more slowly. Ironically, even though blue stars are relatively rare, they play outsized roles in cosmic evolution because they process and redistribute material so aggressively. They are stellar engines of change. Inside their cores, fusion progresses beyond hydrogen much more rapidly than in smaller stars. Once hydrogen becomes depleted, massive stars continue fusing heavier elements in successive stages. Helium fusion produces carbon and oxygen. Carbon fusion produces neon, sodium, and magnesium. Further stages create silicon, sulfur, calcium, and eventually iron. Each stage occurs more rapidly than the last. Hydrogen burning may last millions of years. Silicon fusion near the end may last only days. This accelerating progression happens because heavier fusion reactions produce less energy per reaction, while requiring increasingly extreme temperatures. Massive stars effectively race toward disaster, and throughout all this, hydrostatic equilibrium becomes increasingly difficult to maintain. Radiation pressure inside blue stars is enormous. Their cores approach conditions where stability becomes fragile. Pulsations, instabilities, and mass loss grow increasingly important. Some massive stars rotate extremely rapidly as well. Rapid rotation changes stellar structure significantly. Centrifugal effects can flatten stars into oblate shapes, lowering surface gravity near the equator. One famous example is Achernar. Achernar spins so rapidly that its equatorial diameter becomes dramatically larger than its polar diameter. Stars, it turns out, do not always remain neatly spherical. Massive stars also generate intense magnetic fields and complex internal convection zones. Their interiors become turbulent environments where radiation transport, plasma flows, and nuclear reactions interact continuously. Even their surfaces are violent. Blue stars often exhibit strong stellar winds moving at thousands of kilometers per second. Material blasted outward from these stars enriches surrounding interstellar space long before final supernova explosions occur. And because they are so luminous, blue stars can be observed across enormous cosmic distances. Astronomers use massive blue stars as indicators of active star-forming regions inside galaxies. Young galaxies undergoing intense star formation often contain large populations of hot, luminous blue stars. The presence of many blue stars tells astronomers something important immediately. The region is young. Massive stars die quickly, so any galaxy still containing large numbers of them must have formed stars relatively recently. In contrast, older stellar populations become dominated by smaller, longer-lived stars after massive stars disappear. Blue stars therefore act almost like cosmic age markers. Their existence announces recent stellar birth. But despite their brilliance, these stars are surprisingly fragile in certain ways. Massive stars sit closer to physical limits, where radiation pressure competes strongly against gravity. In extremely massive stars, radiation pressure can become so intense that it destabilizes outer layers significantly. Some stars approach what astronomers call the Eddington limit, the point where outward radiation pressure nearly balances inward gravity. Near this threshold, stars become unstable and lose mass rapidly. One especially famous example is Eta Carinae. Eta Carinae is among the most extreme stellar systems known. During the 19th century, it underwent a giant eruption that temporarily made it one of the brightest stars in Earth's sky. The eruption expelled enormous quantities of material into surrounding space, and remarkably, the star survived. For now. Astronomers expect Eta Carinae eventually to explode as a supernova, or perhaps even a hypernova, producing one of the most dramatic stellar deaths possible. Massive blue stars spend their entire lives approaching such catastrophic endings. Their brilliance comes at the cost of stability and longevity. Physics demands balance. Higher luminosity requires higher fusion rates. Higher fusion rates consume fuel rapidly. Rapid fuel consumption shortens stellar lifetimes dramatically. The universe does not permit massive stars to remain calm for very long, and from a biological perspective, this matters enormously. Planetary systems around very massive stars likely struggle to support long-term complex evolution simply because the stars evolve too quickly. Even if suitable planets formed, the star itself may explode before advanced life has time to emerge. Again, time becomes central. Stable complexity requires long durations of relatively predictable conditions. Massive blue stars instead create dynamic, high-radiation environments evolving rapidly on cosmic timescales. Still, their importance cannot be overstated. Nearly all elements heavier than helium ultimately owe their existence to stellar nucleosynthesis inside stars, especially massive stars. The oxygen humans breathe, the calcium in bones, the silicon in rocks, the iron in blood, much of it originated in massive stellar interiors or supernova explosions. Blue stars are destructive, but they are also creative. Without generations of massive stars forming and dying, galaxies would remain chemically primitive places filled mostly with hydrogen and helium. Complex planets and life would never emerge. For most people looking up at the night sky, stars appear mostly white. A few may look slightly reddish, others might seem faintly blue. But unless conditions are especially dark and clear, the human eye does not easily distinguish subtle stellar colours. Our vision simply is not optimized for careful nighttime spectroscopy. Evolution apparently decided that avoiding cliffs in low light mattered more than accurately identifying stellar surface temperatures. Astronomers, however, learned long ago that star colour reveals something profoundly important: temperature. And once scientists understood the relationship between temperature and starlight, the entire logic behind stellar classification began making sense. At first glance, the connection between colour and heat may seem counterintuitive. On Earth, people often associate red with higher temperatures because of flames, warning lights, or overheated electronics. But in astrophysics, blue stars are actually hotter than white stars, which are hotter than yellow stars, which are hotter than orange and red stars. The reason comes directly from blackbody radiation physics. Any object above absolute zero emits electromagnetic radiation. The hotter the object becomes, the more energy it radiates, and the shorter the wavelengths at which emission peaks. This behaviour follows a relationship known as Wien's law. As temperature increases, peak emission wavelength decreases. Cooler objects emit more strongly, at longer red and infrared wavelengths. Hotter objects shift toward blue and ultraviolet wavelengths. The same physics explains why heated metal glows dull red first, then orange, yellow, white, and eventually bluish-white at extreme temperatures. Stars simply operate on vastly larger scales. White stars occupy an especially interesting region in this sequence because they sit near temperatures where visible light emission becomes broadly balanced across multiple wavelengths. Rather than strongly favouring red or blue, they emit substantial energy throughout much of the visible spectrum, producing a white appearance. And importantly, white stars are not all identical. Some are ordinary main sequence stars, others are giant stars, some are white dwarfs, dense stellar remnants entirely different from normal hydrogen-burning stars. This is where stellar classification becomes more nuanced than simple colour labels. Astronomers classify stars primarily using spectral classes O, B, A, F, G, K, M. That sequence reflects decreasing surface temperature. O stars are hottest and blue. M stars are coolest and red. White stars often belong to the A or early F classes, though exact appearance depends on temperature, luminosity, atmospheric composition, and observational conditions. A-type stars especially are classic white stars. Their surface temperatures typically range between about 7,500 and 10,000 Kelvin. At those temperatures, hydrogen absorption lines become particularly strong in stellar spectra. That detail turns out to be very important. Early astronomers initially found stellar spectra somewhat confusing, because hydrogen lines do not simply grow stronger with increasing temperature forever. Instead, hydrogen absorption reaches maximum prominence in A-type stars. At lower temperatures, hydrogen atoms lack sufficient excitation. At higher temperatures, hydrogen becomes ionized, removing electrons necessary for certain absorption transitions. A-type stars occupy the ideal middle ground where hydrogen absorption lines appear strongest. This discovery helped astronomers realize that spectral classification primarily reflected temperature rather than chemical composition differences. One famous example of a white A-type star is Sirius A. Sirius A is the brightest star visible in Earth's night sky. Located relatively nearby at about 8.6 light-years away, it shines with a brilliant white-blue appearance. Physically, Sirius A is larger, hotter, and more luminous than the Sun. Its surface temperature approaches roughly 9,900 Kelvin, making it substantially hotter than our G-type yellow star. And Sirius A has an especially interesting companion. Orbiting it is Sirius B, one of the first white dwarfs ever discovered. This pairing became historically important because it revealed something astonishing about stellar remnants. Sirius B possessed roughly the Sun's mass compressed into a volume similar to Earth's size. At first, astronomers struggled to understand how such an object could exist physically. The answer eventually led toward quantum degeneracy pressure and entirely new branches of astrophysics. But before reaching white dwarfs properly, it helps to stay with ordinary white stars for a moment. Another famous A-type white star is Vega. Vega has played an important role throughout astronomical history. It served as a standard reference star for brightness measurements, and was among the first stars photographed besides the Sun. Physically, Vega rotates extremely rapidly, so rapidly in fact that centrifugal effects distort its shape significantly. The star bulges outward near the equator, producing temperature variations across its surface. Its poles become hotter and brighter than equatorial regions. Stars are not always neat uniform spheres. Rapid rotation complicates stellar structure considerably. A third important white star is Altair. Altair spins even faster than Vega, completing a rotation in only about 9 hours. For comparison, the Sun rotates approximately once every 25 days near its equator. That rapid rotation flattens Altair visibly. Interferometric imaging actually resolved the star's distorted shape directly. This was a remarkable achievement because stars normally appear too distant to image in detail. And again, temperature differences emerge across the surface due to rotation-induced gravity variations. Where gravity weakens near the equator, temperatures drop slightly. Physics keeps linking everything together. Mass, rotation, gravity, temperature, radiation. Stellar properties continuously interact rather than behaving independently. Then there is Deneb. Deneb differs dramatically from Vega or Sirius, because it is not a main sequence star at all. It is a supergiant. This highlights another important point. Stars with similar surface temperatures can possess enormously different sizes and luminosities. Deneb's surface temperature resembles that of some ordinary white stars, yet its luminosity exceeds the Sun's by hundreds of thousands of times because of its immense size. Luminosity depends not only on temperature, but also on surface area. A huge, moderately hot star can outshine a smaller, hotter star simply because it radiates across vastly larger regions. The Stefan-Boltzmann law captures this relationship. L equals 4 PR squared sigma T to the power of 4 luminosity increases with surface area and temperature. The temperature term becomes especially powerful because luminosity scales with the 4th power of temperature. Even modest temperature increases dramatically affect stellar brightness. That is why hot stars radiate so intensely. And this also explains why white stars can vary enormously in intrinsic luminosity despite sharing broadly similar colours. Spectral class alone does not tell the full story. Astronomers therefore introduced luminosity classes alongside spectral types. A star classified as A1V is a main sequence star. A 1-3 indicates a giant. A 1IA identifies a luminous supergiant. These combined classifications encode substantial physical information compactly. Spectra themselves reveal much more than temperature alone. Pressure broadening affects absorption lines depending on stellar surface gravity. Chemical abundances alter spectral features. Magnetic fields, rotation and motion all influence observed light. Astronomers effectively learned how to decode stellar atmospheres remotely using spectroscopy. That achievement still feels extraordinary. By analysing tiny shifts and patterns in starlight, scientists determine temperatures, chemical compositions, velocities, magnetic activity, rotation rates, and evolutionary stages for stars impossibly distant from Earth. Everything comes from photons, small packets of light crossing enormous regions of space carrying encoded physical information. And white stars help to reveal much of this because their spectra display strong hydrogen features so clearly. A-type stars became especially important calibration object throughout astrophysical history. But there is another category of white stars that behaves entirely differently from ordinary hydrogen-burning stars: white dwarfs. And despite sharing the word white, these objects are fundamentally separate from main sequence white stars. A white dwarf is not a normal star at all. It is a stellar remnant left behind after lower mass stars exhaust nuclear fuel and shed outer layers. Without fusion generating outward pressure, gravity compresses the remaining core enormously. Yet collapse eventually halts because of quantum mechanical effects, specifically electron degeneracy pressure. This creates incredibly dense objects. A white dwarf may contain roughly solar mass compressed into Earth-like dimensions. Densities become extraordinary. A teaspoon of white dwarf matter would outweigh mountains on Earth. The physics governing such objects differs entirely from ordinary stellar interiors. Fusion no longer powers the star. Instead, white dwarfs simply radiate stored thermal energy gradually over billions of years while cooling slowly. One famous white dwarf is again Sirius B. Another important example is Procyon b. Observations of white dwarfs help confirm predictions of quantum mechanics and relativistic stellar structure theories during the 20th century. At first, their existence seemed physically impossible, because ordinary gas pressure could not support such dense objects against gravity. Quantum degeneracy pressure solved the mystery. According to the Pauli exclusion principle, electrons cannot occupy identical quantum states simultaneously. Compress matter enough, and electrons resist further compression through quantum mechanical effects alone. The universe occasionally resorts to remarkably strange solutions, and white dwarfs eventually led astronomers toward even more extreme stellar remnants, because there is a limit to how much mass electron degeneracy pressure can support. That limit, calculated by Subrahmanyan Chandrasekhar, is approximately 1.4 solar masses. Above the Chandrasekhar limit, white dwarfs collapse further. That collapse eventually produces neutron stars or black holes depending on mass, so even the study of white stars quietly points toward far more extreme astrophysics waiting ahead. But returning to ordinary stellar colours for a moment, the broader classification sequence reveals a profound truth about stars. Colour is temperature. Temperature reflects internal physics. Internal physics depends primarily on mass. A star's visible appearance therefore becomes a clue to deep processes hidden inside its core. A cool red dwarf burns fuel slowly. A white A-type star radiates more intensely. A hot blue O-type star races rapidly toward destruction. The night sky may look visually calm from Earth, but every visible star represents a different balance of gravity, pressure, fusion, and time. And once astronomers understood spectral classes properly, stars stopped being isolated points of light and became measurable physical systems evolving according to universal laws. That realization transformed astronomy completely. The heavens no longer resembled a static decorative dome above Earth. Instead, they became dynamic populations of evolving objects with lifetimes, temperatures, internal structures, and eventual deaths. For most of a star's life, hydrogen fusion in the core provides stability. Gravity pulls inward, fusion pushes outward. Hydrostatic equilibrium keeps the star balanced for millions, billions, or even trillions of years depending on mass. But this arrangement contains a hidden problem from the very beginning. Hydrogen fuel is finite. Every second, stable stars convert enormous amounts of hydrogen into helium. Slowly, almost imperceptibly on human timescales, the composition of the stellar core changes. Helium accumulates while hydrogen becomes depleted, and eventually, after unimaginably long periods of stability, the core reaches a turning point. Hydrogen fusion begins to fail, not instantly, not dramatically at first, but the balance maintaining the star starts changing fundamentally. This transition creates one of the most important stages in stellar evolution, the giant phase, and despite the name, giant stars are not necessarily more massive than they once were. In fact, many giant stars have already begun losing material through stellar winds. They become giant because their outer layers expand enormously. The underlying physics behind this expansion is subtle and surprisingly counterintuitive. At first glance, you might expect fusion slowing in the core to make the star shrink and cool permanently. Gravity should begin winning once outward pressure weakens, and initially that is partly true. As hydrogen in the core becomes exhausted, fusion rates there decrease. Without sufficient outward thermal pressure, gravity compresses the core further inward. But compression raises temperature. That detail changes everything. The contracting helium core grows hotter under increasing gravitational pressure. Surrounding layers of hydrogen outside the exhausted core also become compressed and heated. Eventually, hydrogen fusion ignites in a shell surrounding the helium core, and shell fusion behaves differently from ordinary core fusion. It can produce substantially more energy. The increased outward energy flow pushes the star's outer layers dramatically outward. The atmosphere expands enormously. Surface area increases massively. But because the surface spreads across a much larger volume, surface temperature often decreases even while total luminosity rises. The star becomes larger, brighter, and redder. A giant star is born. One of the best-known examples is Aldebaran. Aldebaran appears as a bright orange-red star in Earth's night sky. Although only slightly more massive than the Sun originally, it has expanded enormously during its giant phase. If Aldebaran replaced the Sun, its outer atmosphere would extend inward toward the orbit of Mercury and possibly beyond. And yet its surface temperature is cooler than the Sun's. That combination surprises many people initially. Giant stars become extremely luminous, not because their surfaces are necessarily hotter, but because they possess such enormous radiating surface areas. Again, the Stefan-Boltzmann law becomes important. L equals 4, PR squared sigma T to the power of 4 luminosity depends on both temperature and surface area. A huge cool star can outshine a much smaller hot star simply through sheer size. And giant stars truly become enormous. Another famous example is Arcturus. Arcturus is among the brightest stars visible from Earth and represents a later evolutionary stage for a once ordinary main sequence star. Compared to the Sun, Arcturus has expanded dramatically and now radiates more than 100 times greater luminosity. Inside, its structure differs profoundly from that of a stable main sequence dwarf. The helium core continues contracting and heating, while hydrogen shell fusion powers the surrounding layers. This creates increasingly complex stellar interiors. The Sun itself will eventually undergo this transformation. Roughly 5 billion years from now, after exhausting core hydrogen, the Sun will leave the main sequence and begin expanding into a red giant. Its outer atmosphere may engulf Mercury and Venus entirely. Earth's ultimate fate remains somewhat uncertain, because stellar mass loss and orbital evolution complicate predictions. But conditions here would certainly become catastrophic long before direct engulfment became relevant. Oceans would evaporate, atmospheric chemistry would collapse, surface temperatures would rise enormously, the familiar solar system would become unrecognizable. Fortunately, this remains comfortably far in the future. Human beings are remarkably skilled at worrying about immediate deadlines, despite the Sun not reaching red giant status for another several billion years. Still, giant star evolution reveals an important truth about stellar equilibrium. Stars are not static objects. Even during apparently calm periods, they evolve continuously because fusion changes internal composition over time. Hydrogen becomes helium. Helium accumulation alters pressure, density, and temperature conditions. Eventually, entirely new fusion behaviours emerge, and giant phases are only the beginning. For Sun-like stars, the contracting helium core eventually reaches temperatures around 100 million Kelvin. At those extreme conditions, helium fusion ignites through the triple alpha process. This reaction combines helium nuclei into carbon. The ignition of helium fusion can become extraordinarily dramatic in smaller giant stars. In stars roughly similar to the Sun, the helium core becomes electron degenerate before helium ignition begins. Degenerate matter behaves strangely, because pressure no longer depends strongly on temperature. Normally hotter gas expands and cools, stabilizing fusion. Degenerate matter does not respond that way. As a result, helium ignition can occur explosively in an event called the helium flash. Despite the name, this does not destroy the star externally. Most of the energy goes into lifting core degeneracy and restructuring the stellar interior, rather than blasting the atmosphere away. Still, internally, the event is astonishingly energetic. For a brief period, helium fusion rates may exceed the luminosity of entire galaxies. Stars occasionally handle ridiculous amounts of energy quite casually. After helium ignition stabilizes, the star enters a somewhat calmer phase temporarily, but the internal structure remains layered and increasingly complicated. Fusion shells develop. Core composition changes again. Outer layers continue expanding and becoming unstable, and giant stars become highly dynamic environments. Many pulsate. Surface layers rise and fall rhythmically due to changing pressure balances and opacity effects inside the atmosphere. Some variable giant stars physically expand and contract over repeating cycles. One famous example is Mira. Mira changes brightness dramatically over periods of months because its outer layers pulsate substantially. At maximum brightness, Mira becomes easily visible to the naked eye. At minimum brightness, it can nearly disappear from ordinary observation. Astronomers studying variable giants learned enormous amounts about stellar interiors because pulsations reveal information about density, temperature, and structure hidden beneath the atmosphere. Stars, in a sense, ring like enormous cosmic instruments. Giant stars also begin losing significant mass through stellar winds. Their outer atmospheres become loosely bound because expansion lowers surface gravity. Radiation pressure, pulsations, convection, and magnetic effects help drive material outward into surrounding space. These winds can become surprisingly powerful. Over time, sun-like giant stars may lose substantial fractions of their total mass before finally ejecting outer layers entirely. This mass loss matters enormously for galactic chemistry. Giant stars enrich interstellar space with carbon, nitrogen, oxygen, and other heavier elements produced during fusion. Without stellar winds and later planetary nebula formation, much of that material would remain trapped inside stars. Again, stellar evolution becomes part of cosmic recycling. Elements formed inside stars eventually return to interstellar space where future stars and planets incorporate them. Some of the carbon atoms inside your body likely passed through giant star atmospheres billions of years ago. That statement remains deeply strange every time you pause to think about it properly. Humans often imagine stars as distant and separate from ordinary life, but chemically speaking, Earth is built from recycled stellar material. And giant stars play crucial roles in distributing those materials across galaxies. Observationally, giant stars become much easier to detect than ordinary dwarf stars because of their enormous luminosities. A giant may outshine the sun by hundreds or thousands of times. As a result, giant stars appear prominently across large regions of the night sky, even when relatively distant. Many familiar bright stars are giants, or evolved stars rather than ordinary main-sequence dwarfs. Another famous example is Pollux. Pollux likely began life as a moderately more massive main-sequence star before evolving into its current giant phase. Interestingly, Pollux also hosts an exoplanet, demonstrating that planetary systems can survive at least portions of giant star evolution. Though surviving does not necessarily mean thriving, as stars expand and luminosity changes dramatically, planetary climates and orbital dynamics can become severely disrupted. Inner planets may be engulfed entirely. Outer icy worlds may temporarily warm. Moons may experience altered radiation environments. Entire solar systems evolve alongside their stars. And the larger the original stellar mass, the more extreme giant evolution becomes. Massive stars do not merely become ordinary giants, they evolve into supergiants and hypergiants, reaching sizes almost difficult to visualize comfortably. But even for moderate giant stars, convection becomes enormous. Inside the Sun, convective cells exist but remain relatively small compared to the star's full diameter. In giant stars, convection zones can become gigantic. Surface granulation patterns may span substantial fractions of the entire stellar radius. The atmospheres themselves become diffuse and unstable. Some giant stars possess densities and outer layers lower than laboratory vacuums on Earth. Despite their enormous size, they can become remarkably tenuous near the surface. This creates peculiar observational effects too. Stellar atmospheres may extend across vast distances while remaining extremely thin. Surface boundaries become less sharply defined compared to smaller stars. Stars, it turns out, become increasingly messy as they age. The neat, stable equilibrium of the main sequence gradually gives way to layered fusion shells, pulsations, mass loss, and atmospheric instability. And eventually, for stars like the Sun, giant evolution reaches another endpoint. After helium becomes exhausted, smaller stars cannot raise core temperatures high enough to ignite carbon fusion efficiently. Gravity compresses the carbon-oxygen core further, but not enough for continued large-scale fusion. At that point, outer layers drift away into space. The remaining core becomes a white dwarf. But more massive stars continue onward into even more extreme stages. Because giant stars are not the final stage of stellar evolution. If ordinary stars are long-term balancing acts between gravity and fusion, then supergiants and hypergiants are what happens when that balance starts becoming dangerously difficult to maintain. These are among the largest and most luminous stars in the universe. Some possess radii hundreds or even thousands of times larger than the Sun. Others emit millions of times more energy. Their interiors operate under such extreme conditions that the distinction between stability and instability begins to blur. Radiation itself becomes powerful enough to fight gravity directly in ways smaller stars never experience. And because of that, supergiants live fast, evolve violently, and spend much of their existence on the verge of catastrophic failure. To understand why, it helps to begin with a deceptively simple question. Why do massive stars become unstable in the first place? The answer starts with luminosity. Massive stars generate extraordinary amounts of energy because their cores reach incredibly high temperatures and pressures. Fusion rates increase dramatically with core temperature, especially once the CNO cycle dominates hydrogen burning. As a result, luminosity rises steeply with mass. A star only 20 or 30 times more massive than the Sun may radiate hundreds of thousands of times more energy. The most extreme hypergiants can exceed solar luminosity by millions of times. That energy has consequences. Photons carry momentum. Normally in smaller stars, radiation pressure contributes only part of the outward support balance in gravity. Gas pressure dominates most of the structure. But inside supergiants and hypergiants, radiation pressure becomes enormous. Photons streaming outward from the core collide continuously with stellar material, transferring momentum outward. In extremely luminous stars, this radiation pressure grows so strong that it begins competing seriously with gravity itself. This introduces a dangerous problem. If outward radiation becomes too powerful, the star starts losing mass through stellar winds and eruptive instability. Layers near the surface may no longer remain securely gravitationally bound. Astronomers describe this threshold using the Eddington limit. The Eddington luminosity represents the point where outward radiation pressure balances inward gravitational attraction for ionized gas. Above this limit, radiation pressure can effectively overcome gravity and drive intense mass loss. Supergiants and hypergiants often operate uncomfortably close to this boundary, and the closer a star approaches the Eddington limit, the less stable its outer layers become. One of the most famous examples is Betelgeuse. Betelgeuse is enormous. If placed at the centre of our solar system, its atmosphere would likely extend beyond the orbit of Mars. Yet despite its vast size, its density is astonishingly low in outer layers. Some regions of the atmosphere are more diffuse than laboratory vacuums on Earth. This reveals something important about supergiants. They are not gigantic because they contain solid or dense material filling huge volumes. Instead, their atmospheres become incredibly expanded and tenuous. Betelgeuse itself is a red supergiant nearing the later stages of stellar evolution. Its surface temperature is relatively cool, roughly around 3,500 Kelvin, giving it a reddish appearance. But because its radius is so enormous, it still radiates vastly more energy than the Sun overall. Inside, however, conditions are anything but calm. The core has already progressed far beyond ordinary hydrogen fusion. Massive stars evolve rapidly through successive fusion stages, creating layered interiors somewhat resembling onions. Hydrogen burns in outer shells. Helium fuses deeper inside. Further inward, carbon, neon, oxygen, and silicon fusion may occur depending on evolutionary stage. Each layer contributes to a highly dynamic and unstable structure. And unlike smaller stars, supergiants do not remain in any single stable phase for very long. Their enormous masses force increasingly extreme core temperatures. Fusion accelerates, energy transport intensifies, radiation pressure rises, mass loss grows stronger. These stars effectively spend their lives rushing toward collapse. Another extraordinary example is Antares. Antares resembles Betelgeuse in many ways: immense radius, relatively cool surface temperature, and late-stage stellar evolution. Observations of stars like Antares reveal gigantic convection cells across their surfaces. Unlike the relatively fine granulation visible on the Sun, convection in red supergiants can occur on scales comparable to large fractions of the star itself. Imagine a boiling surface where individual convective regions become larger than entire stellar diameters of smaller stars. The atmospheres of these objects are turbulent and chaotic. Pulsations ripple through them. Material rises and falls. Shockwaves propagate outward. Stellar winds carry away huge quantities of gas. Supergiants are not quiet objects, and once stars move into even more extreme luminosity ranges, they become hypergiants. Hypergiants represent some of the most luminous and unstable stars known. One particularly famous example is VY Canis Majoris. For years, VY Canis Majoris was considered one of the largest known stars. Although improved measurements revised some earlier estimates downward, it remains an astonishing object. Its atmosphere extends across truly absurd distances. If placed in the solar system, its outer layers could stretch near or beyond Jupiter's orbit, depending on how one defines the stellar boundary. And importantly, the star is losing mass rapidly. Hypergiants can shed enormous amounts of material through powerful stellar winds and eruptive events. Radiation pressure, pulsations, and atmospheric instability combine to drive matter outward continuously. In some cases, stars may lose several Earth masses of material every year. Astronomy occasionally produces numbers that sound incorrect simply because ordinary human intuition evolved for much smaller environments. The instability of hypergiants becomes especially obvious in luminous blue variables. These stars undergo irregular eruptions where luminosity, temperature, and mass loss can change dramatically. The most famous example is probably Eta Carinae. Eta Carinae is among the most extreme stellar systems known. During the 19th century, it underwent the Great Eruption, temporarily becoming one of the brightest stars visible from Earth, despite lying thousands of light years away. During this event, Eta Carinae expelled enormous quantities of material into surrounding space, forming the spectacular homunculus nebula still observed today, and remarkably, the star survived. The eruption released energy comparable to some smaller supernovae, yet Eta Carinae remained intact, at least for now. Astronomers expect it eventually to die in a catastrophic supernova or hypernova explosion. Inside Eta Carinae, radiation pressure operates at terrifying intensities. The star likely began with well over 100 solar masses, though strong stellar winds have already removed substantial portions of its original mass. This highlights one of the great paradoxes of hypergiants. They begin enormously massive but struggle to remain that way because their own luminosities tear them apart. Radiation pressure effectively becomes self-destructive. The the star shines so intensely that it destabilizes itself. And because mass loss alters stellar structure continuously, modelling these stars becomes extremely difficult. Small changes in opacity, rotation, magnetic fields, or convection can dramatically affect stability. Hypergiants sit near the limits of what stars can physically sustain. Rotation complicates matters further. Many massive stars rotate rapidly. Centrifugal effects reduce effective gravity near the equator, making mass loss easier there. Combined with radiation pressure, this can produce asymmetric winds and distorted stellar shapes. Magnetic fields also influence outflows, and convection in these stars becomes enormous and turbulent. Unlike smaller stars where equilibrium remains relatively smooth, supergiants often behave dynamically and unpredictably. Some exhibit large brightness variations, others undergo episodic eruptions. Still others pulsate rhythmically because internal pressure waves propagate through unstable layers. One especially fascinating class is the Wolf-Rayet stars. These are evolved, massive stars that have lost much of their outer hydrogen envelopes through extreme stellar winds. Their exposed hotter layers emit intense radiation and produce broad spectral emission features. An important example is WR124. Wolf-Rayet stars represent late evolutionary stages of extremely massive stars approaching eventual collapse. Their winds can reach thousands of kilometers per second. Again, these stars are actively tearing themselves apart, and all of this mass loss profoundly affects later stellar evolution. A star's final fate depends strongly on how much mass remains when core collapse begins. Intense winds may reduce some stars enough to alter supernova outcomes significantly. Massive stars therefore evolve through complicated interactions between fusion, gravity, radiation pressure, convection, rotation, and mass loss simultaneously. No simple calm equilibrium lasts very long. Yet despite their instability, supergiants and hypergiants play enormously important roles in cosmic evolution. Their stellar winds enrich surrounding interstellar space with heavy elements. Their ultraviolet radiation shapes nearby molecular clouds. Their eventual supernova explosions seed galaxies with carbon, oxygen, silicon, calcium, iron, and many other elements necessary for rocky planets and biology. Without massive stars, galaxies would remain chemically primitive. In fact, some of the most important elements for life emerge primarily from massive stellar evolution. Oxygen production especially depends strongly on massive stars. The oxygen humans breathe was forged inside stars that likely lived brief, violent lives before exploding long before the sun formed. This connection between stellar instability and biological existence remains one of the strangest truths in astrophysics. Life on Earth depends directly on generations of unstable massive stars dying violently billions of years ago, and supergiants also help astronomers study distant galaxies. Because they are so luminous, they remain visible across enormous distances. Individual supergiants can sometimes be identified in nearby galaxies millions of light years away. Their spectra reveal information about chemical composition, stellar populations, and galactic evolution. Massive stars therefore act as cosmic beacons. And because they evolve rapidly, they trace recent star formation particularly well. A galaxy containing many luminous blue supergiants must have formed stars relatively recently, because such stars do not survive long. Again, timescales matter enormously. A red dwarf may survive trillions of years. A hypergiant may barely persist for a few million. The most massive stars burn themselves toward destruction at extraordinary speeds because their internal conditions become so extreme. Eventually, however, fusion reaches a limit. Iron accumulates in the core, and iron changes the entire equation. Fusion of lighter elements releases energy, because binding energy per nucleon increases up to iron. But iron fusion does not release net energy efficiently. Once massive stars develop iron cores, fusion can no longer provide sufficient outward pressure to counter gravity. At that point, the core collapses catastrophically. and when collapse begins inside a supergiant or hypergiant, the resulting explosion becomes one of the most violent events in the universe, a supernova. When stars like the Sun approach the ends of their lives, they do not explode as supernovae. That fate belongs mostly to much more massive stars. Instead, ordinary stars follow a quieter but no less remarkable path. After expanding into giant phases and shedding enormous amounts of material into surrounding space, they leave behind something small, dense, and deeply strange, a white dwarf. At first glance, white dwarfs seem almost contradictory. They contain masses comparable to the Sun, yet their sizes resemble Earth's. They no longer sustain ordinary fusion reactions, yet many remain incredibly hot for billions of years. Gravity crushes them toward collapse continuously, but somehow they resist further compression without the help of thermal pressure from nuclear burning. The key to understanding white dwarfs lies not in ordinary gas physics, but in quantum mechanics. And this is where stellar astrophysics begins entering territory that feels fundamentally different from everyday intuition. To understand how white dwarfs form, it helps to begin near the end of a Sun-like star's giant phase. As hydrogen fusion ceases in the core, stars evolve into red giants. Helium fusion eventually begins. For moderate mass stars, fusion may proceed through helium-burning stages producing carbon and oxygen in the core. But unlike massive stars, Sun-like stars cannot continue fusion indefinitely. Their gravitational pressures never become high enough to ignite carbon fusion efficiently. Eventually, fusion shells become unstable, and outer layers drift away into surrounding space. These expanding shells often form planetary nebulae. The name is somewhat misleading historically. Early astronomers thought these glowing clouds resembled planets through small telescopes. In reality, they are enormous expanding envelopes of gas illuminated by the exposed hot stellar core remaining at the centre. One beautiful example is the Ring Nebula. Another famous example is the Helix Nebula. At the centre of these nebulae sits the stellar remnant itself, the white dwarf. What remains after the outer atmosphere escapes is essentially the exposed core of the former star, mostly carbon and oxygen compressed into extraordinary density. At this point, ordinary thermal pressure is no longer sufficient to support the object against gravity. Fusion has largely ceased. The core continues cooling over time. So why does collapse stop? The answer involves electron degeneracy pressure, and degeneracy pressure is one of the strangest consequences of quantum mechanics applied to large-scale astrophysics. Ordinary matter allows particles substantial freedom of movement. In gases, particles occupy a range of energy states. Compress the gas and particles move faster, increasing thermal pressure. But electrons obey the Pauli exclusion principle. This principle states that two identical fermions, particles like electrons, cannot occupy the same quantum state simultaneously. Under normal conditions, this rule is not especially noticeable in daily life. Inside white dwarfs, however, gravity compresses matter so intensely that electrons become packed extraordinarily closely together. Eventually, available low-energy quantum states fill up completely. At that point, further compression forces electrons into higher momentum states. This creates pressure independent of temperature, electron degeneracy pressure. And critically, degeneracy pressure does not rely on fusion or ordinary thermal motion. Even a cooling white dwarf continues resisting collapse, because quantum mechanics itself forbids electrons from occupying identical states. This produces one of the most bizarre forms of matter in astrophysics. A white dwarf is effectively supported by quantum mechanical exclusion. Gravity attempts to compress the star further. Quantum mechanics refuses. Equilibrium emerges from that conflict. One of the most famous examples is Sirius B. Sirius B orbits the bright main sequence star Sirius A and became historically important because its properties initially appeared almost impossible. astronomers determined that Sirius B possessed roughly solar mass, yet its luminosity remained extremely faint compared to ordinary stars. The only explanation was extraordinary density. Matter had somehow become compressed far beyond ordinary stellar conditions. At first, scientists struggled deeply with this conclusion, because classical physics alone could not explain how such dense stars resisted collapse. Quantum mechanics solved the problem during the early 20th century. And once electron degeneracy pressure became understood, white dwarfs transformed from mysterious anomalies into fundamental stellar endpoints. The densities involved remain difficult to visualize comfortably. A typical white dwarf may compress mass comparable to the Sun into a volume similar to Earth's. Average densities can exceed millions of grams per cubic centimetre. A teaspoon of white dwarf material would weigh tons on Earth, not metaphorically, literally. Matter inside white dwarfs exists in highly compressed plasma states, where nuclei and electrons become packed extraordinarily tightly together. And yet white dwarfs are not static dead objects entirely. Many begin incredibly hot. Newly formed white dwarfs may possess surface temperatures exceeding 100,000 Kelvin. Without fusion generating fresh energy, however, they gradually cool over billions of years. They are essentially stellar embers slowly radiating away stored thermal energy. Because cooling proceeds extremely slowly, many white dwarfs remain visible for enormous timescales. Eventually, in the unimaginably distant future, white dwarfs should cool into hypothetical black dwarfs, cold dark remnants no longer emitting significant radiation. But the universe is not old enough for any black dwarfs to exist yet. Again, astrophysics routinely deals with timescales exceeding current cosmic history. Another famous white dwarf is Procyon b. Observations of systems like Procyon helped astronomers refine white dwarf mass-radius relationships, and this relationship is especially strange. For ordinary stars, adding mass generally increases size. White dwarfs behave oppositely. More massive white dwarfs become smaller. This counterintuitive behavior emerges directly from degeneracy physics. As mass increases, gravity compresses matter more intensely. Electron degeneracy pressure rises accordingly, but the star contracts further in the process. The result is an inverse mass-radius relation. Add more mass, and the white dwarf shrinks. Physics occasionally enjoys behaving in ways specifically designed to make introductory intuition fail, and there is a limit to how much mass electron degeneracy pressure can support. This limit was calculated by Subramanian Chandrasekhar while he was still remarkably young. The Chandrasekhar limit, approximately 1.4 solar masses, represents the maximum mass-stable electron degeneracy pressure can support against gravity. Above this threshold, collapse resumes. No stable white dwarf can exist beyond it. This discovery was initially controversial because some astronomers disliked its implications. It suggested stars could collapse into even stranger states of matter once white dwarf support failed. Later discoveries of neutron stars and black holes confirmed Chandrasekhar's conclusion spectacularly. But before reaching those extreme objects, white dwarfs themselves already demonstrate astonishing physics. Surface gravity on a white dwarf becomes enormous. A human standing on one would experience impossible gravitational conditions long before any practical concerns about landing arrangements became relevant. The gravitational acceleration can exceed Earth's by factors of hundreds of thousands, and this intense gravity affects light directly. White dwarfs exhibit measurable gravitational redshift predicted by general relativity. Photons climbing away from the strong gravitational field lose energy, shifting slightly toward longer wavelengths. Again, white dwarfs became important testing grounds for fundamental physics. Quantum mechanics, relativity, plasma physics, and stellar evolution all intersect inside these objects, and white dwarfs are extremely common. Because most stars in the galaxy possess relatively low or moderate masses, the vast majority will eventually end as white dwarfs. The the Sun itself will almost certainly become one. Roughly 5 to 7 billion years from now, after giant phases and planetary nebula formation, the solar system's central star will settle into white dwarf existence. Earth, if it survives at all, would orbit a dense stellar remnant gradually cooling over trillions of years. That future is difficult to picture emotionally because human intuition evolved around much shorter timescales. But astrophysics forces perspective changes constantly. Civilizations rise and disappear while stars barely notice, and white dwarfs do not always remain quiet. In binary systems especially, they can become extremely dangerous. If a white dwarf orbits closely with a companion star, gravity may pull material away from the companion onto the white dwarf surface. This accreted hydrogen gradually accumulates under intense gravity. Eventually, temperatures and pressures become high enough to trigger explosive fusion on the surface. A nova occurs. Unlike supernovae, novae do not destroy the white dwarf entirely. Surface explosions eject accumulated material outward, while the underlying remnant survives. These eruptions can repeat repeatedly over time. One famous recurrent nova system is T Coronii Borealis. But if accretion continues long enough, something even more dramatic may happen. A white dwarf approaching the Chandrasekhar limit becomes unstable. Electron degeneracy pressure can no longer support the increasing mass. Carbon fusion may ignite explosively throughout the star nearly simultaneously. The result is a Type 1a supernova. Unlike ordinary core collapse supernova from massive stars, Type 1a supernovae originate from white dwarf instability, and these explosions are extraordinarily important in cosmology. Because Type 1a supernovae occur near consistent masses, they reach relatively predictable peak luminosities. Astronomers use them as standard candles to measure enormous cosmic distances. Observations of distant Type 1, a supernova eventually revealed one of the greatest discoveries in modern astronomy. The expansion of the universe is accelerating. Dark energy entered cosmology partly because exploding white dwarfs exposed it observationally. Again, seemingly specialized stellar physics ended up reshaping humanity's understanding of the entire cosmos. White dwarfs therefore occupy an unusual position in astrophysics. They are stellar corpses, but they remain scientifically alive with importance. They test quantum mechanics, they influence binary evolution, they enrich interstellar space through novae, they help measure cosmic expansion. And eventually, many may crystallize internally as they cool. Yes, crystallize. As temperatures fall sufficiently, carbon and oxygen nuclei inside white dwarfs may arrange themselves into crystalline lattice structures. Astronomers have found evidence suggesting some white dwarfs contain enormous crystallized interiors, essentially gigantic cosmic diamonds forming slowly over billions of years. The universe occasionally drifts into territory that sounds suspiciously fictional, despite being entirely legitimate astrophysics. And white dwarfs also reveal something profound about stellar evolution more generally. Gravity never stops. Fusion only temporarily delays collapse. Throughout a star's life, gravity continuously attempts to compress matter further inward. Main sequence stability exists only because fusion produces enough pressure to counteract that compression. Once fusion weakens, collapse resumes. White dwarfs represent one possible stopping point where quantum mechanics intervene successfully. White dwarfs already push matter into conditions far beyond anything encountered in ordinary experience. Electrons become degenerate. Gravity reaches enormous intensities. Entire stellar masses compress into planetary dimensions, and yet, for sufficiently massive stars, even that is not enough. When the collapsing core exceeds the Chandrasekhar limit, electron degeneracy pressure fails. Gravity continues inward relentlessly. Temperatures surge. Densities climb to astonishing levels. And at some point during this catastrophic collapse, matter itself changes form. Electrons and protons are forced together so violently that they combine into neutrons through inverse beta decay. Protons and electrons merge into neutrons while neutrinos stream outward in enormous numbers. The collapsing stellar core effectively transforms into a gigantic atomic nucleus, supported not by electron degeneracy pressure anymore, but by neutron degeneracy pressure and strong nuclear interactions. A neutron star is born, and neutron stars are among the most extreme physical objects in the observable universe. Typical neutron stars contain around 1.4 to perhaps 2 solar masses compressed into spheres only about 20 kilometers across. 20 kilometers. That is smaller than many cities. Matter reaches densities so extraordinary that a teaspoonful brought to Earth would weigh billions of tons, not millions. Billions. The human brain does not naturally possess intuition for objects like this because nothing remotely comparable exists in everyday life. A neutron star is essentially a collapsed stellar core where gravity has overwhelmed ordinary atomic structure completely. Inside normal matter, atoms contain vast amounts of empty space. Electrons occupy diffuse quantum orbitals around tiny nuclei. If atoms were compressed enough to remove most empty space, density would rise enormously. Neutron stars go much further. Gravity crushes matter past white dwarf conditions until individual nuclei themselves begin merging into continuous nuclear matter. The resulting object behaves less like ordinary material and more like an immense quantum fluid governed by nuclear physics, and remarkably, collapse still stops. Why? Again, quantum mechanics intervenes. Neutrons obey the Pauli exclusion principle, just like electrons do. They cannot all occupy identical quantum states simultaneously. As densities rise, neutron degeneracy pressure increases dramatically, resisting further compression, at least temporarily. Because neutron stars also sit near another boundary, where gravity threatens to win entirely. But before reaching black holes, neutron stars themselves produce astonishing physics. One famous example is PSRB 1919+21. Its discovery in 1967 transformed astrophysics almost overnight. Initially, the object appeared as an extremely regular series of radio pulses arriving every 1.337 seconds with astonishing precision. The signals were so oddly regular that researchers jokingly labelled the source LGM-1 for Little Green Men. Fortunately for science fiction enthusiasts everywhere, alien civilizations turned out not to be responsible. The pulses originated from a rapidly rotating neutron star. This revealed another extraordinary property of neutron stars. They spin incredibly fast. During stellar collapse, conservation of angular momentum dramatically increases rotation rates. The same principle allowing ice skaters to spin faster by pulling inward applies here, though on vastly more terrifying scales. A massive stellar core collapsing from millions of kilometers across down to roughly 20 kilometers spins up enormously. Some neutron stars rotate several times per second, others spin hundreds of times per second. The fastest known millisecond pulsars complete rotations in fractions of milliseconds. Surface velocities can approach substantial fractions of light speed, and because neutron stars possess intense magnetic fields, rotating charged particles generate focused beams of electromagnetic radiation. If those beams sweep across Earth, astronomers detect regular pulses, hence the name Pulsars. One of the most famous pulsars is Crab Pulsar. The Crab Pulsar formed during a supernova explosion observed by Chinese astronomers in 1054 CE. The resulting Crab Nebula still expands outward today, while the neutron star at its centre spins roughly 30 times per second. Every rotation sends pulses of radiation sweeping through space like a cosmic lighthouse. And remarkably, pulsars are extraordinarily precise, some rival atomic clocks in rotational stability. Again, the universe enjoys combining chaos and precision in strange ways. The supernova explosion producing the neutron star is among the most violent events in existence. During core collapse, the stellar core implodes at enormous speeds. electrons combine with protons, neutrinos flood outward, densities soar, and eventually the collapsing inner core stiffens suddenly under neutron degeneracy pressure. The rebound, combined with intense neutrino heating, helps drive the outer layers outward in a catastrophic supernova explosion. For a brief period, the dying star may outshine entire galaxies. Most of the explosion's energy actually leaves in neutrinos. This is one of the strangest details about core collapse supernovae. Visible light represents only a tiny fraction of the total energy released. Neutrinos carry away most of it. During supernova collapse, neutron star formation produces such extraordinary neutrino fluxes that trillions pass through your body during supernova 1987A without you noticing. Neutrinos interact so weakly with matter that entire stars barely slow them down, and neutron stars left behind after these explosions continue evolving in fascinating ways. Surface gravity becomes extraordinary. A person standing on a neutron star, ignoring several immediate practical problems like radiation, magnetic fields, and being instantly compressed into unrecognizable matter, would experience gravity billions of times stronger than Earth's. General relativity becomes crucial under such conditions. Time itself runs measurably slower near neutron star surfaces because gravity curves space-time intensely. Light escaping the surface becomes gravitationally redshifted. Space and time behave differently near these objects, and then there are the magnetic fields. Neutron stars often possess staggeringly strong magnetism because magnetic flux conservation amplifies fields enormously during collapse. Compress a star while preserving magnetic flux, and field strength skyrockets. Some neutron stars become magnetars, objects possessing the strongest magnetic fields known in the universe. One famous example is SG 1806-20. Its magnetic field is so powerful that if placed halfway to the Moon, it could disrupt electronic systems and distort atomic structures on Earth. Close proximity would not end well for biology. Magnetar fields may exceed 10 to the 11th power Tesla. For comparison, MRI machines on Earth typically operate around a few Tesla. Again, astrophysics routinely produces numbers so extreme they barely feel meaningful emotionally. Inside neutron stars, matter itself enters poorly understood states. Outer layers form dense crusts of nuclei immersed in degenerate electrons. Deeper regions likely contain superfluid neutrons and superconducting protons. Still deeper, the exact physics remains uncertain. Theoretical models suggest possibilities including hyperons, pion condensates, quark matter, or even more exotic phases. Neutron stars therefore function as natural laboratories for nuclear physics impossible to recreate fully on Earth. No human experiment can compress matter to neutron star densities over macroscopic scales. The universe performs the experiment for us, and astronomers learn by observing rotational behavior, gravitational effects, thermal emission, magnetic activity, and neutron star collisions. Collisions became especially important recently. In 2017, astronomers observed gravitational waves from a merging neutron star binary, GW170817. This event transformed astrophysics. For the first time, scientists observed both gravitational waves and electromagnetic radiation from the same cosmic collision. The merger produced enormous amounts of heavy elements, including gold and platinum. This solved another major mystery. Where do many of the universe's heaviest elements originate? The answer appears to involve neutron-rich environments created during neutron star mergers. Gold jewelry, platinum electronics, and many rare heavy elements on Earth may ultimately trace their origins to ancient neutron star collisions billions of years ago. The universe truly commits to dramatic methods of chemical production, and neutron star mergers themselves are astonishingly violent. As two neutron stars spiral together through gravitational wave emission, orbital speeds approach relativistic values. Tidal forces distort both objects. Magnetic fields interact chaotically. Then collision occurs. Enormous quantities of neutron-rich matter eject outward, while space-time itself ripples violently. The resulting explosion, a kilonova, briefly shines with tremendous brightness, while freshly synthesized heavy elements decay radioactively. Human beings eventually learned about the origins of gold by observing dead stars colliding at relativistic speeds. Science occasionally sounds entirely unreasonable despite being correct. Neutron stars also reveal something profound about gravity. These objects exist precariously near the threshold where collapse into black holes becomes unavoidable. There is another upper mass limit beyond which neutron degeneracy pressure and nuclear forces cannot resist gravity successfully. This is the Tolman-Oppenheimer-Volkoff limit, though its exact value remains uncertain because ultra-dense nuclear matter physics remains incompletely understood. Above this threshold, collapse continues indefinitely. No known force halts it. A black hole forms. Neutron stars therefore occupy a narrow region between white dwarfs and black holes, dense enough to destroy ordinary atomic structure, yet not dense enough for total gravitational collapse. They are transitional objects balanced at extreme physical limits, and despite their bizarre physics, neutron stars remain detectable across enormous distances because of their powerful emissions. Pulsars sweep radio beams through space. Magnetars produce X-ray and gamma-ray bursts. Accreting neutron stars in binary systems emit intense high-energy radiation, as in falling matter heats enormously before impact. One especially famous binary neutron star system is Hulse-Taylor binary. Observations of this system confirmed predictions from general relativity because orbital energy decreased precisely as expected from gravitational wave emission. Long before gravitational waves were directly detected, neutron stars already provided indirect evidence that spacetime itself radiates energy through gravity. Again, these objects continuously intersect multiple branches of physics simultaneously: quantum mechanics, relativity, nuclear physics, plasma physics, magnetohydrodynamics. Particle physics, all operating together under conditions impossible to reproduce artificially. And neutron stars still cool gradually over time. Young neutron stars begin extraordinarily hot, but because of their tiny surface areas relative to ordinary stars, they radiate differently. Neutrino cooling inside the core also becomes important during early stages. Over millions of years, they fade gradually, but even cooling neutron stars remain astonishingly dense remnants of catastrophic stellar death. When neutron stars were first predicted theoretically, they already sounded extreme enough. A stellar remnant with more mass than the Sun compressed into a sphere roughly the size of a city should have been sufficient for astrophysics to quietly stop escalating the situation further. Instead, neutron stars turned out to possess additional properties that pushed them into entirely new levels of physical absurdity. Some rotate hundreds of times every second. Some generate magnetic fields so powerful they distort atomic structure itself. Some emit beams of radiation with such regular precision that astronomers use them as cosmic clocks. Others release sudden bursts of high-energy radiation, capable of briefly outshining enormous regions of the galaxy. These objects are pulsars and magnetars, and they represent some of the most energetic and extreme stellar remnants in the known universe. To understand why pulsars behave the way they do, it helps to begin with angular momentum. Conservation of angular momentum is one of the most powerful principles in physics. It appears everywhere from spinning tops to orbiting planets, and during stellar collapse, it becomes absolutely dramatic. Imagine a massive star rotating relatively slowly before collapse. Even a modest rotation rate contains substantial angular momentum because the star's radius is enormous. Then the core collapses from millions of kilometers across down to perhaps 20 kilometers. Angular momentum must remain conserved. The result is enormous spin-up. The same principle allows figure skaters to rotate faster when pulling their arms inward. but neutron star collapse compresses stellar cores by truly extraordinary factors. A star rotating once every several days before collapse may become a neutron star rotating many times per second afterward. Some spin far faster. One of the fastest known pulsars, PSR J1748-2 446 AD, rotates over 700 times every second. 700 every second. Surface velocities near the equator approach significant fractions of light speed. And importantly, neutron stars do not merely rotate quickly, they also possess intense magnetic fields. During collapse, magnetic flux conservation amplifies magnetic strength enormously. Compress magnetic field lines into a vastly smaller volume and field intensity skyrockets. The resulting neutron star may possess magnetic fields trillions of times stronger than Earth's. Now combine rapid rotation with powerful magnetism. Charged particles trapped near the neutron star accelerate along magnetic field lines, producing intense electromagnetic radiation. Because the magnetic axis usually does not align perfectly with the rotational axis, radiation beams sweep through space as the star spins. If one of those beams crosses Earth, astronomers detect pulses, hence the name pulsar. The first pulsar discovered, PSRB 1919+21, initially confused astronomers profoundly because its radio pulses arrived with astonishing regularity. The intervals were so precise that researchers briefly considered artificial origins. After all, nature rarely behaves with such clock-like precision. Except, apparently, neutron stars. Pulsars quickly became some of the most accurate natural clocks known. Their rotational stability can rival atomic clocks over long periods. Each pulse represents a rotating beam sweeping across Earth exactly once per rotation. And because neutron stars possess enormous rotational energy, these beams can remain detectable for millions of years. The rotational kinetic energy involved is extraordinary. A simplified rotational energy relation looks like this: E sub rot equals 1/2 E omega squared, where I is moment of inertia and omega is angular velocity. Neutron stars possess huge moments of inertia and enormous angular velocities simultaneously. Even tiny decreases in rotation rate release tremendous amounts of energy. Over time, pulsars gradually slow down as radiation carries energy away. Astronomers can measure this slowdown extremely precisely. One famous example is the Crab pulsar. The Crab pulsar rotates roughly 30 times per second and powers much of the surrounding nebula's energetic emission. Observations show the pulsar steadily losing rotational energy while spinning down gradually over time. And because pulsars are so precise, they became useful for testing fundamental physics. Tiny irregularities in pulse timing reveal remarkable information. Astronomers detect exoplanets orbiting pulsars through timing variations. They measure gravitational effects. They test general relativity. They even use pulsar timing arrays to search for passing gravitational waves. Again, stellar remnants become laboratories for multiple branches of physics simultaneously. One especially important system is Hulse-Taylor binary. This binary neutron star system provided indirect evidence for gravitational waves decades before direct detections became possible. As the two neutron stars orbit one another, they emit gravitational radiation predicted by Einstein's general relativity. Orbital energy decreases gradually, causing the stars to spiral inward slowly. Observations matched theoretical predictions with astonishing precision. Gravity itself appeared to radiate energy exactly as relativity demanded. All because astronomers monitored the timing of pulses from a rotating dead star. Pulsars also come in multiple varieties. Young pulsars like the Crab pulsar rotate rapidly after recent supernova formation. Older pulsars gradually slow down over millions of years, but some old pulsars become recycled through binary interactions. If a neutron star accretes matter from a companion star, In falling, material transfers angular momentum, spinning the neutron star back up to enormous rotation rates. These become millisecond pulsars. One famous example is PSRJ 0437-4715. Millisecond pulsars can rotate hundreds of times per second with astonishing stability. And despite the violence of their origins, neutron stars themselves remain incredibly small. That compactness intensifies every aspect of their physics. Gravity becomes extreme, magnetic fields become extreme, rotational effects become extreme, energy densities become extreme. Even tiny surface irregularities can produce enormous observable consequences, because conditions are already operating near physical limits. Then there are magnetars, and magnetars push neutron star physics into still more unreasonable territory. A magnetar is essentially a neutron star possessing an extraordinarily powerful magnetic field, not merely strong by ordinary neutron star standards, truly extreme. Typical neutron star magnetic fields may reach around 10 to the 8th power Tesla. Magnetars may exceed 10 to the 11th power Tesla. These are the strongest magnetic fields known anywhere in the universe. One particularly famous example is SGR 1806-20. In 2004, SGR 1806-2 produced one of the most powerful giant flares ever observed. The burst briefly released more energy in a fraction of a second than the Sun emits in hundreds of thousands of years. Even from tens of thousands of light years away, the flare affected Earth's ionosphere measurably, and the event originated from a single neutron star. Magnetars derive their energy primarily from magnetic field decay rather than rotation alone. As their immense magnetic fields evolve and rearrange internally, enormous stresses build within the crust. Eventually the crust may fracture suddenly in starquakes. These fractures release huge bursts of X-rays and gamma rays. The resulting eruptions become some of the brightest high-energy events in the galaxy, and magnetar-magnetic fields become strong enough to alter atomic physics itself. Near a magnetar surface, atoms may become elongated along magnetic field lines. Vacuum polarization effects predicted by quantum electrodynamics become important. Even empty space behaves differently under such conditions. Quantum field theory itself enters observable astrophysics. Again, neutron stars continuously push physics into regimes unavailable anywhere else. Another famous magnetar is 1E1048.1-5937. Objects like this emit intense X-ray radiation and display irregular bursts connected to magnetic activity. The distinction between pulsars and magnetars is not always absolute either. Some neutron stars display mixed behaviors depending on age, field strength and rotational properties. Nature enjoys categories less than textbooks do. And neutron stars also generate powerful relativistic particle winds. Pulsar winds consist of charged particles accelerated to near-light speeds by electromagnetic processes surrounding the rotating neutron star. These winds interact with surrounding supernova remnants, producing spectacular structures visible across multiple wavelengths. The Crab Nebula remains one of the best examples. At the centre, the pulsar injects enormous energy into surrounding material continuously. Jets, filaments, shock waves, and synchrotron radiation all emerge from these interactions. Pulsars therefore remain dynamically important long after the original supernova explosion fades. And because neutron stars possess such intense gravity, relativistic effects become unavoidable near their surfaces. Time dilation becomes measurable, light bends strongly. Matter accreting onto neutron stars in binary systems heats enormously before impact, producing intense X-ray emission. One famous X-ray binary containing a neutron star is Scorpius X1. Matter pulled from the companion star forms an accretion disk, spiraling inward under extreme gravity. Friction and compression heat the material to millions of degrees before it crashes onto the neutron star surface. These systems become among the brightest X-ray sources in the sky, and unlike black holes, neutron stars possess actual physical surfaces. Accreting matter eventually impacts solid crust. This distinction allows certain observational tests separating neutron stars from black holes. Still, neutron stars remain close to the edge of complete collapse. The exact internal structure remains uncertain because ultra-dense nuclear matter physics is incompletely understood. Some theories predict exotic phases deep inside neutron stars. Possibilities include superfluid neutrons, superconducting proton layers, hyperons, pion condensates, or even deconfined quark matter. The core conditions may approach densities exceeding those inside atomic nuclei themselves. And if enough additional mass accumulates, neutron degeneracy pressure eventually fails entirely. Collapse resumes, a black hole forms. Neutron stars therefore occupy a narrow region between stable stellar remnants and total gravitational collapse. They represent matter compressed almost as far as the universe allows, without destroying space-time structure completely. Almost. But even before black holes enter the story, pulsars and magnetars already reveal something profound about the universe. The laws of physics remain consistent even under absurdly extreme conditions. Quantum mechanics still governs particles, relativity still governs gravity, electromagnetism still shapes radiation. The same equations describing laboratory physics on Earth continue operating inside rotating stellar corpses with magnetic fields powerful enough to distort atomic structure. The universe does not require separate rules for extreme environments. Ordinary laws simply continue into extraordinary territory. And somewhere tonight, hidden among the stars, countless neutron stars continue spinning silently through darkness. Some sweep radio beams across space with perfect precision. Some crack under magnetic stress and release gamma-ray flares. Some slowly spiral toward collisions that will shake space-time itself. And some may eventually collapse further still, crossing the final boundary where even neutron matter can no longer resist gravity. The threshold of black holes. For a very long time, astronomy treated stars and planets as completely separate categories. Stars produced light through nuclear fusion. Planets did not. The distinction seemed straightforward enough. A star was a star. A planet was a planet. The universe appeared comfortably organized into separate boxes. Then astronomers started discovering objects that refused to fit neatly into either category. They were larger than planets, sometimes far larger. Some possessed masses dozens of times greater than Jupiter's. Yet they failed to sustain ordinary hydrogen fusion like true stars. They glowed faintly. They emitted heat. Some briefly fused unusual isotopes early in life. But they never became stable main-sequence stars. These strange objects became known as brown dwarfs, and they occupy one of the most fascinating middle grounds in astrophysics, suspended awkwardly between giant planets and true stars. In a sense, brown dwarfs are failed stars. Though failed may be slightly unfair. Gravity pulled gas inward. Collapse began. Temperatures rose. The object formed normally from molecular clouds, much like ordinary stars do. But somewhere during the process, the growing protostar simply did not accumulate enough mass to ignite sustained hydrogen fusion. The result is an object permanently trapped between stellar and planetary physics. To understand brown dwarfs properly, it helps to begin with the minimum mass required for ordinary stellar fusion. Hydrogen nuclei repel one another electrically because they carry positive charge. Fusion only becomes possible when temperatures and pressures rise high enough for nuclei to approach closely enough that the strong nuclear force overcomes electrostatic repulsion. That requires enormous conditions. Inside ordinary stars, gravity compresses the core sufficiently to achieve temperatures of millions of Kelvin. Once the core exceeds roughly 10 million Kelvin, sustained hydrogen fusion begins, but there is a critical threshold. Objects below approximately 0.08 solar masses, around 75 to 80 times Jupiter's mass, generally cannot sustain stable hydrogen fusion in their cores. Gravity simply cannot compress them strongly enough. The core may become extremely hot, but not hot enough. Fusion never stabilizes. The object becomes a brown dwarf instead. That threshold marks one of the most important dividing lines in astrophysics. Above it, stars. Below it, substellar objects. And because brown dwarfs never achieve sustained hydrogen burning, they evolve very differently from true stars. Ordinary stars spend most of their lives in hydrostatic equilibrium. Fusion generates pressure balancing gravity. Luminosity remains relatively stable over enormous timescales. Brown dwarfs never reach that stable long-term balance. Instead, they slowly cool and fade over time. Initially, young brown dwarfs can appear surprisingly hot and luminous, because gravitational contraction releases significant thermal energy during formation. Some also briefly fuse deuterium, a heavy isotope of hydrogen containing one proton and one neutron. Deuterium fusion requires lower temperatures than ordinary hydrogen fusion. Brown dwarfs above roughly 13 Jupiter masses may sustain deuterium fusion temporarily during early evolution. But the available deuterium supply is limited. Fusion eventually ceases. Afterward, the brown dwarf simply radiates away stored thermal energy gradually over billions of years. In other words, brown dwarfs do not truly shine the way stars do. They cool, slowly, continuously. And because they cool steadily, older brown dwarfs become extremely faint and difficult to detect. This made them frustratingly elusive for astronomers. For decades, scientists strongly suspected brown dwarfs should exist theoretically, but observational confirmation remained difficult. These objects emit little visible light and radiate primarily in infrared wavelengths. Before infrared astronomy became sufficiently advanced, brown dwarfs essentially hid in the darkness between stars. Finally, during the 1990s, convincing discoveries arrived. One of the earliest confirmed examples was Tidal. Its discovery provided critical evidence that nature indeed produces objects occupying the mass range between planets and stars. Soon afterward, astronomers began finding many more, and once better infrared surveys appeared, brown dwarfs started showing up everywhere. The universe apparently produces enormous numbers of almost stars. One especially famous example is Lumen 16. Located only about 6.5 light-years away, Lumen 16 is among the closest known systems to the Sun. It contains two brown dwarfs orbiting one another, allowing astronomers to study atmospheric behavior and cloud patterns directly. And brown dwarf atmospheres are fascinatingly strange. Because their temperatures overlap partially with giant planets, complex chemistry becomes important. Instead of ordinary stellar atmospheres dominated purely by ionized plasma, cooler brown dwarfs develop clouds made from exotic materials: silicate clouds, iron droplets, metallic condensates. At certain temperatures, minerals literally rain through the atmosphere. Astrophysics occasionally drifts into sounding like speculative fiction, despite remaining entirely legitimate science. Another important brown dwarf is Gliese 229b. Gliese 229b became especially significant because its spectrum revealed strong methane absorption, similar to giant planets like Jupiter. This discovery highlighted how blurry the boundary between planets and brown dwarfs could become observationally. And indeed, classification remains somewhat complicated. Brown dwarfs and giant planets may overlap in mass ranges depending on formation history. Astronomers increasingly distinguish them not only by mass, but also by formation mechanism. Stars and brown dwarfs generally form through direct gravitational collapse inside molecular clouds. Planets usually form within protoplanetary disks surrounding stars. The distinction matters because formation history influences structure and composition. Still, the universe rarely respects neat categories perfectly. Some giant exoplanets approach brown dwarf masses. Some brown dwarfs resemble giant planets spectroscopically. Nature continues quietly ignoring humanity's desire for tidy definitions. Brown dwarfs also introduced entirely new spectral classes beyond the traditional stellar sequence. Ordinary stars follow the familiar O, B, A, F, G, K, M sequence, but cooler brown dwarfs required additional categories L, T and Y. L dwarfs remain relatively warm and display metal hydride absorption along with dusty atmospheres. T dwarfs cool enough for methane absorption to dominate spectra. Y dwarfs become even colder, approaching temperatures comparable to some planets. One especially remarkable example is Y's 0855-0714. Its temperature may fall below the freezing point of water. A failed star, colder than many places on Earth. That statement alone demonstrates how unusual brown dwarf evolution becomes. Unlike ordinary stars that maintain steady luminosities through fusion, brown dwarfs simply continue cooling indefinitely. Young brown dwarfs may initially resemble dim red stars. Old brown dwarfs fade toward planetary temperatures. Time changes them dramatically. And because they are fully convective internally, their structures differ from stars like the Sun. Convection circulates material throughout much of the interior. Heat transport occurs efficiently through bulk fluid motion rather than radiative zones dominating large regions. Magnetic activity also becomes interesting. Some brown dwarfs generate surprisingly strong magnetic fields and produce radio emissions despite relatively cool temperatures. Auroral processes somewhat analogous to planetary auroras may occur. Again, these objects blur stellar and planetary physics continuously. One particularly fascinating aspect of brown dwarfs is their size. Counterintuitively, many brown dwarfs remain similar in radius to Jupiter despite possessing vastly greater masses. This happens because electron degeneracy pressure begins influencing internal structure. As mass increases, gravity compresses the object more strongly, but degeneracy effects resist expansion. The result is surprisingly small radius variation across broad mass ranges. Some brown dwarfs, dozens of times more massive than Jupiter, remain only slightly larger physically. Matter under these conditions behaves differently from ordinary gas spheres, and eventually at sufficiently high masses near the hydrogen-burning threshold, the distinction between the largest brown dwarfs and the smallest red dwarf stars becomes remarkably subtle. Tiny differences in mass determine whether sustained fusion ignites or not. That threshold itself depends somewhat on composition too. Metallicity influences opacity and core conditions, slightly altering minimum stellar masses. The universe operates through continuous physical transitions more often than sharp boundaries. Brown dwarfs also appear surprisingly common. Some estimates suggest they may rival stars in abundance numerically, though because they are faint, counting them accurately remains difficult. Infrared surveys continue discovering new nearby brown dwarfs, even relatively close to the solar system. It is entirely possible that undiscovered brown dwarfs still drift nearby on galactic scales. And because they emit little visible light, ancient humans would never have known they existed. For most of human history, the night sky displayed only ordinary stars visible to the naked eye. Entire populations of dim substellar objects remained hidden entirely until modern infrared astronomy revealed them. That realization remains slightly unsettling. The solar neighborhood contains objects invisible to human eyes despite existing relatively nearby. The universe always contains more than immediate perception suggests. Brown dwarfs also sometimes host planetary systems. One remarkable example is 2 MAS SJ 04414488 plus 23011513. Observations like these demonstrate that disk formation and companion formation occur naturally even around substellar objects. In principle, planets may orbit failed stars. Imagine standing on a moon, orbiting a brown dwarf. The sky would look profoundly different from Earth's. there would be little visible starlight from the primary object. Instead, the brown dwarf might glow dim reddish or infrared, perhaps invisible to human eyes entirely depending on temperature and age. Cloud bands of silicates or metals could swirl through the atmosphere. Auroral emissions might illuminate surrounding darkness occasionally. It would be an extraordinarily alien environment. And because brown dwarfs cool continuously, habitable conditions near them become difficult to maintain long term. Unlike stars, they do not provide stable energy output over billions of years. Their luminosities decline steadily. Still, brown dwarfs remain scientifically invaluable because they connect multiple branches of astrophysics. They bridge planetary science and stellar astronomy. They test atmospheric models under unusual conditions. They probe low-temperature chemistry. They help constrain theories of star formation and mass distribution inside molecular clouds. And they demonstrate something fundamental about nature. Not every gravitational collapse produces a true star. Sometimes the universe gathers enormous quantities of gas together, only to stop just short of ignition. Almost enough gravity, almost enough pressure, almost enough heat, but not quite. And once fusion fails to stabilize, gravity and quantum mechanics settle into a different compromise. Brown dwarfs contract partially, heat temporarily, then cool slowly across cosmic timescales. Neither fully stellar nor fully planetary, objects suspended between categories, and importantly, brown dwarfs remind astronomers that stellar classification is not simply a list of isolated types. Instead, stars, substellar objects, giants, remnants, pulsars, and hypergiants all emerge from the same underlying physical laws applied under different conditions. Mass changes the outcome. Everything else follows. Too little mass and fusion never fully ignites. Moderate mass produces long-lived stable stars. Extreme mass creates luminous, unstable giants racing toward collapse. And after all these different stellar lives unfold, one final realization begins emerging. Stars are not separate phenomena scattered randomly through space. They are stages within a single continuous story driven by gravity, nuclear physics, quantum mechanics, radiation, and time itself. And once you step back far enough, every star type in the universe begins revealing something much larger than individual objects alone. The universe is teaching the same physical lesson repeatedly, simply at different scales. For much of human history, people imagined stars as isolated objects scattered individually across space. One star here, another there. Tiny distant lights existing independently from one another. That assumption turned out to be spectacularly wrong. Many stars do not live alone at all. In fact, binary and multiple star systems are extremely common throughout the galaxy. Large numbers of stars form together inside collapsing molecular clouds, and gravity frequently leaves them bound in orbital relationships lasting millions or billions of years. Some pairs remain widely separated and relatively calm. Others orbit so closely that they distort one another physically, exchange matter, trigger explosions, emit gravitational waves, and evolve through interactions far more complicated than anything isolated stars experience. And once astronomers began studying these systems carefully, stellar evolution suddenly became much stranger. Because stars do not merely evolve according to their own masses, companions can interfere. Mass transfer can completely rewrite stellar futures. Gravity can reshape entire evolutionary pathways. Binary interactions can produce objects impossible for single stars to create alone. In a sense, exotic stellar systems reveal what happens when astrophysics stops behaving politely. One of the simplest examples is an ordinary visual binary system, where two stars orbit a common centre of mass while remaining widely separated. The nearest stellar system to Earth beyond the Sun, Alpha Centauri, is actually a multiple star system. Alpha Centauri A and Alpha Centauri B orbit one another, while the red dwarf Proxima Centauri orbits farther away. This immediately demonstrates something important. The Sun is not necessarily representative of all stellar systems. A large fraction of stars exist in binaries or larger gravitational arrangements, and once stars become close enough together, their interactions become dramatically important. Gravity distorts stellar shapes, matter transfers between stars, orbital energy evolves, rotation changes, magnetic interactions emerge. The system stops behaving like two independent stars and instead becomes a coupled physical environment. One especially important concept here is the Roche lobe. Every star in a binary system possesses a region where its gravity dominates surrounding space. If a star expands enough to overflow this region, matter can spill toward the companion star through gravitational interaction. This changes everything. Mass transfer allows one star to feed another, and depending on the nature of the recipient object, the consequences range from unusual to catastrophic. For example, consider a binary system where one star evolves into a white dwarf, while the companion continues ordinary stellar evolution. As the companion expands into a giant phase, material may begin flowing toward the white dwarf. Hydrogen accumulates on the white dwarf's surface under enormous gravity. Eventually, fusion ignites explosively. A nova occurs. One famous recurrent nova system is T Coronae Borealis. This system periodically brightens dramatically when accumulated hydrogen detonates on the white dwarf's surface. Unlike supernovae, novae do not destroy the white dwarf entirely. The cycle may repeat repeatedly over long periods, but if enough matter accumulates, the white dwarf may eventually approach the Chandrasekhar limit. At that point, electron degeneracy pressure fails. Carbon fusion ignites catastrophically throughout the star. A Type 1, a supernova results. And these explosions are enormously important because their relatively consistent luminosities allow astronomers to measure cosmic distances. Observations of distant Type 1a supernovae eventually reveal that cosmic expansion is accelerating, one of the great discoveries leading toward dark energy, all because binary stars exchange matter in very particular ways. Again and again, stellar interactions end up influencing cosmology itself. Another extraordinary category involves X-ray binaries. These systems contain neutron stars or black holes accreting matter from companion stars. Material spirals inward through accretion disks, heating enormously because of friction and gravitational compression. Temperatures may rise into millions of degrees. The result is intense X-ray emission. One famous example is Cygnus X1. Cygnus X1 became historically important as one of the first strong black hole candidates ever identified. Matter falling toward the compact object emits powerful X-rays before disappearing beyond the event horizon. Nearby, the companion star continues orbiting while gradually losing material. These systems are astonishingly energetic. Accretion physics around neutron stars and black holes becomes among the most efficient energy generation mechanisms in the universe. Infalling matter converts gravitational potential energy into radiation extremely effectively. And because compact objects possess intense gravity, relativistic effects become unavoidable. Time dilation, gravitational redshift, relativistic jets, orbital precession, all emerge naturally near these environments. Another famous X-ray binary is Scorpius X1. Unlike Cygnus X1, the compact object here is a neutron star rather than a black hole. Matter crashing onto the neutron star surface releases enormous energy through X-ray emission. And because neutron stars possess physical surfaces while black holes do not, observational differences emerge between the two systems. Binary interactions also produce some of the universe's most accurate gravitational laboratories. One of the most famous examples is Hulse-Taylor binary. This system contains two neutron stars orbiting one another. One acts as a pulsar, producing extraordinarily precise timing signals. Astronomers observed the orbital period slowly decreasing over time, exactly as predicted by Einstein's general relativity. The system was losing energy through gravitational wave emission. Long before direct gravitational wave detectors existed, binary pulsars already confirmed that spacetime itself carries energy through ripples in gravity. This was one of the great triumphs of modern physics, and eventually some compact binaries spiral together completely. As neutron stars or black holes orbit closely, gravitational waves carry energy away continuously. The orbit shrinks, velocities increase, tidal forces intensify. Finally, collision occurs. One especially historic event was GW170817. For the first time, astronomers observed both gravitational waves and electromagnetic radiation from the same cosmic merger. The collision produced a kilonova, an explosion powered partly by radioactive decay of newly synthesized heavy elements. Gold, platinum, rare heavy nuclei. Many of the universe's heaviest elements appear to originate in environments like these. Again, astrophysics casually explains jewelry through relativistic neutron star collisions. And binary systems are not the only source of stellar weirdness. Some stars become variable because of internal instability rather than external companions. Variable stars change brightness over time for many different reasons. Some pulsate physically, others erupt unpredictably. Some vary because eclipsing companions block light periodically. Still others fluctuate because of magnetic activity or accretion processes. One famous class is the Cepheid variables. These stars pulsate rhythmically because internal ionization layers create unstable pressure cycles. The mechanism involves helium ionization changing opacity inside the stellar atmosphere. As layers compress, opacity increases, trapping heat and increasing pressure. Expansion follows, cooling reduces opacity. Gravity pulls inward again. The cycle repeats. One famous example is delta Cepheid. Cepheid variables became critically important because their pulsation periods correlate directly with intrinsic luminosity. Astronomers can measure the pulsation period, determine true luminosity, compare with apparent brightness, and calculate distance. This relationship allowed humanity to measure distances across the galaxy, and eventually to other galaxies. Without Cepheid variables, modern cosmology would have developed far more slowly. Again, stellar behavior reshaped humanity's understanding of cosmic scale. Another important class is Aurora Lyrae variables, often used for mapping older stellar populations. Then there are mirror variables like Mira, where giant stars expand and contract dramatically over long periods. Mira's brightness changes enormously because the star physically pulsates. At maximum brightness, it becomes visible to the naked eye. At minimum brightness, it nearly vanishes. The star is literally breathing on stellar scales, and some variable systems become deeply chaotic. Cataclysmic variables involve accretion instabilities, magnetic interactions, and explosive outbursts. Luminous blue variables like Eta Carinae undergo gigantic eruptions, shedding huge quantities of mass unpredictably. Eta Carinae's great eruption during the 19th century temporarily made it one of the brightest stars in the sky, despite lying thousands of light years away. The eruption expelled enormous nebula structures still visible today. The star survived. Barely. Binary interactions may even influence its future evolution significantly, and then there are contact binaries. In these systems, stars orbit so closely that their outer atmospheres physically touch. Material flows continuously between them. Shapes become distorted into elongated forms by tidal gravity. One famous example is W Ursae Majoris. The stars effectively share outer envelopes. Again, nature refuses to maintain clean separations between categories. Some binaries eventually merge completely. Stellar mergers can produce unusual objects like blue stragglers, Stars appearing younger and hotter than surrounding stellar populations suggest they should be. Blue stragglers likely form through collisions or mass transfer rejuvenating older stars. Clusters therefore contain stars whose apparent ages no longer match ordinary expectations. Interactions rewrite evolutionary histories, and in dense stellar environments like globular clusters, gravitational encounters become frequent enough that stars may exchange companions, eject one another, or collide directly. The centers of some clusters behave almost like crowded gravitational ecosystems. Stellar dynamics becomes chaotic. Compact objects encounter ordinary stars. Binary systems form and break apart. Neutron stars get recycled into millisecond pulsars through accretion. Exotic systems emerge naturally from repeated gravitational interactions. One especially fascinating class involves relativistic jets. Accreting neutron stars and black holes sometimes launch narrow beams of plasma moving near light speed. Magnetic fields threading accretion disks appear to channel enormous energies into these collimated outflows. One famous microquasar example is SS433. Jets from SS433 move at roughly 1/4 light speed, and because the system precesses, the jets trace changing orientations through space over time. The amount of energy concentrated into such narrow beams becomes astonishing. Scaled-up versions of similar physics likely power quasars at galactic centers. Again, stellar-scale systems help explain galactic-scale phenomena, and importantly, exotic stellar systems reveal that the universe is not merely a collection of isolated objects evolving independently. Interaction matters. Gravity couples systems together. Companions alter destinies. Mass transfer changes stellar lifetimes. Relativity reshapes orbital evolution. Entirely new classes of objects emerge from combinations impossible for single stars alone. This complexity also means astronomers must think statistically. A star's fate depends not only on its mass, but also on whether companions exist, how close the orbit is, whether mass transfer occurs, how rotation evolves, and how gravitational interactions unfold over millions or billions of years. Stellar evolution becomes less like a simple diagram, and more like an enormous branching network of possible outcomes. And despite all this complexity, the same physical laws continue governing everything. Gravity drives orbital motion, fusion powers stars, quantum mechanics supports compact remnants, relativity shapes strong gravitational systems, electromagnetism drives radiation and magnetic interactions. The equations never fundamentally change, the environments simply become more extreme, and somewhere tonight, across the galaxy, countless exotic systems continue evolving silently. White dwarfs steal matter from companions, neutron stars sweep radio beams across space, black holes consume accretion disks, binary pulsars spiral gradually inward. Variable stars pulse rhythmically through darkness. Stars exchange matter, collide, explode, merge, and reshape one another continuously, all while the galaxy itself slowly rotates around the Milky Way center. And after exploring all these different stellar lives, from faint brown dwarfs to collapsing neutron stars, from stable yellow suns to eruptive hypergiants, one final question naturally remains. What does the existence of all these different star types actually tell us about the universe itself? If you step outside late at night and look upward long enough, something very strange eventually begins happening to your sense of scale. At first, the stars feel familiar. Small lights above the horizon, patterns humans have named for thousands of years, constellations, bright points, a quiet sky. But after spending enough time learning what stars actually are, the night changes completely. Those lights stop feeling simple. You begin realizing that every visible star overhead represents a different balance of gravity, fusion, pressure, radiation, quantum mechanics, and time. Some are quietly conserving fuel for trillions of years. Others are moments away from collapse. Some are already dead remnants cooling silently through darkness. Others are interacting violently with companions, distorting space-time itself through gravitational waves, and all of them exist simultaneously inside the same galaxy. That realization changes the meaning of the night sky, because stars are not merely background scenery for human life. They are the engines shaping the universe itself. Every atom heavier than hydrogen and helium had to come from somewhere. The early universe after the Big Bang contained mostly hydrogen, helium, and trace amounts of lithium. That was enough to create the first stars, but not enough to create rocky planets, oceans, atmospheres, biology, or human beings. Everything else came later, inside stars. And this is perhaps the most important thing every stellar type reveals collectively. The universe evolves, not metaphorically, physically, chemically, structurally. The cosmos changes over time because stars continuously transform matter from simpler forms into more complex ones. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, neon, silicon, sulfur, calcium, iron. Supernovae scatter those elements outward. New stars form from enriched gas. Planets emerge around later stellar generations. Eventually chemistry becomes complicated enough for life. Without stars, the universe would remain chemically primitive forever. No rocky worlds, no atmosphere like Earth's, no biology, no people sitting awake at night wondering what stars are. In a very literal sense, stellar evolution made complex existence possible, and every type of star contributes differently to that story. Red dwarfs reveal the power of patience. These small stars burn fuel so slowly and efficiently that none have died naturally yet because the universe itself remains too young. They remind us that cosmic timescales stretch far beyond ordinary intuition. Human civilizations rise and disappear while red dwarfs barely change. The smallest stars may outlive galaxies in recognizable forms. That alone forces perspective changes. Human history often feels ancient from within ordinary life. 1,000 years seems enormous. 10,000 years feels almost unimaginable emotionally. But stars casually operate across billions and trillions of years. The universe is not rushed. Yellow and orange dwarfs reveal stability. Stars like the Sun maintain hydrostatic equilibrium for immense stretches of time, balancing gravity and fusion with astonishing reliability. Around at least one such star, chemistry became biology, and biology eventually became self-aware. That may turn out to be common throughout the galaxy, or extraordinarily rare. Astronomers still do not know, but stable stars provided the time necessary for complexity to emerge gradually. Without long-term stellar stability, Earth's biosphere could never have evolved into its current form. Blue giants and supergiants reveal the opposite lesson. Power comes at the cost of longevity. Massive stars burn hotter, brighter, and faster because gravity forces their cores into extreme conditions. Their brilliance is extraordinary, but their lifetimes become short. And despite their brief existence, they reshape galaxies. They ionize nebulae, they trigger star formation, they create heavier elements, they explode violently. Massive stars act like cosmic accelerators driving rapid change throughout interstellar space. Without them, galaxies would evolve far more slowly. White dwarfs reveal something deeply strange about matter itself. Fusion ends, gravity compresses matter inward, and quantum mechanics intervenes. Electron degeneracy pressure prevents further collapse even though ordinary thermal pressure disappears. A white dwarf is essentially a stellar corpse supported by quantum exclusion principles. That sentence would have sounded completely absurd to ancient astronomers. It still sounds slightly absurd now, and yet it is true. Neutron stars push the story further. Gravity overwhelms ordinary atomic structure entirely. Electrons and protons merge into neutrons. Matter becomes compressed beyond anything humans can recreate artificially. Neutron stars reveal physics operating near the limits of what matter can survive without collapsing completely into black holes. Pulsars and magnetars reveal that even dead stars can remain astonishingly active. Rotation, magnetic fields, relativity, quantum mechanics, all interacting simultaneously. Some neutron stars become clocks more accurate than many human technologies. Others generate magnetic fields strong enough to distort atomic structure itself. The universe continues functioning consistently, even under conditions almost impossible to visualize comfortably. Brown dwarfs reveal something equally important. Not every collapse succeeds. Some objects gather enormous quantities of gas but stop just short of sustained fusion. Almost stars. Substellar objects suspended between planetary and stellar physics. The existence of brown dwarfs reminds us that nature rarely organizes itself into perfect categories. Boundaries blur, transitional states appear, physics operates continuously rather than through neat human labels, and exotic binary systems reveal perhaps the most chaotic lesson of all. Stars influence one another. Companions exchange mass. White dwarfs trigger supernovae. Neutron stars spiral together. Black holes consume matter from neighbouring stars. Entire stellar destinies change because gravity connects objects together dynamically. The universe is not built from isolated systems. Interaction matters. Again and again throughout stellar astrophysics, the same fundamental principles repeat. Gravity compresses matter. Pressure resists collapse, fusion releases energy, mass determines fate, and from those simple rules emerges astonishing complexity. That may be the deepest lesson stars reveal. The universe does not require separate laws for every phenomenon. A relatively small set of physical principles generates enormous diversity naturally. Tiny red dwarfs, blue hypergiants, white dwarfs, neutron stars, black holes, all emerge from the same underlying physics applied under different initial conditions. Complexity grows from consistency. And perhaps that is one reason stars affect people so strongly emotionally even before understanding the science. The night sky feels meaningful partly because it connects the ordinary human scale to something vastly larger and older. Stars existed before Earth formed. They will continue existing long after humanity disappears. The atoms inside your body passed through ancient stellar interiors long before the sun existed. That realization changes the relationship between people and the cosmos. Humans are not separate observers standing outside the universe looking inward. We are products of cosmic evolution itself. Hydrogen formed after the Big Bang. Stars forged heavier elements. Those elements formed planets. Planetary chemistry eventually produced living systems capable of studying stellar evolution. The universe became capable of observing itself through matter arranged by stellar physics. There is something quietly remarkable about that chain of events, and perhaps even stranger, the same laws governing distant stars also govern ordinary reality here on Earth. Gravity pulling an apple downward follows the same fundamental interaction governing stellar collapse. Quantum mechanics stabilizing atoms also stabilizes white dwarfs. Relativity shaping neutron star gravity also shapes the expansion of the universe itself. The cosmos is not divided into separate local and celestial physics anymore. Everything belongs to the same system. That realization transformed astronomy permanently. Ancient observers saw stars as mysterious lights beyond Earth. Modern astrophysics revealed them as physical objects obeying understandable laws. Yet strangely, the universe did not become less beautiful after explanation. If anything, it became more astonishing. Knowing that Betelgeuse is a red supergiant nearing collapse does not make it less impressive. Knowing that pulsars are rotating neutron stars emitting relativistic beams does not diminish them. Knowing that every calcium atom in your bones once passed through stellar interiors billions of years ago only deepens the sense of connection. Science did not remove wonder from the night sky, it expanded it. And importantly, the story is still incomplete. Astronomers continue discovering new stellar systems, new exoplanets, new transient events, and new forms of extreme astrophysics constantly. Questions remain unresolved. What exactly happens inside neutron star cores? How do magnetic fields evolve in magnetars? What determines the precise upper mass limits of stars? How common is life around red dwarfs? What unknown forms of stellar interaction remain undiscovered? The universe continues withholding answers faster than humans can fully solve them. That is part of what makes astronomy feel endless. There is always another scale beyond the current one, another mystery behind the visible layer, another region of space-time behaving in ways not fully understood yet. And meanwhile, overhead tonight, the galaxy continues its quiet activity regardless of whether anyone is watching. Stars are forming inside molecular clouds, others are exhausting hydrogen in their cores, white dwarfs are cooling, neutron stars are spinning. Binary systems are exchanging matter. Supernova remnants are expanding. Gravitational waves are crossing space. Entire stellar lifetimes are unfolding silently above Earth every moment. Human beings notice only tiny fragments of it. Yet even those fragments have already reshaped civilization profoundly. Navigation, calendars, physics, chemistry, relativity, quantum mechanics, cosmology. The study of stars transformed humanity's understanding of reality itself. And perhaps the most humbling realization of all is this. The universe did not evolve for us. Stars are not there to illuminate human sky specifically. Fusion began inside stars billions of years before life emerged on Earth. Galaxies collided long before humans existed. Neutron stars spun through darkness while dinosaurs walked across the planet. The cosmos is not centered around human existence, and oddly enough, many people find that comforting rather than depressing. There is relief in realizing the universe is larger than individual worries. Stars continue evolving regardless of politics, deadlines, arguments, or daily anxieties. Gravity does not panic. Fusion does not rush. Galaxies do not become stressed because meetings ran too long. The cosmos simply continues, quietly, patiently. And tonight, somewhere above you, every type of star we discussed still exists. Tiny red dwarfs conserving fuel, stable yellow stars warming planetary systems, blue giants burning recklessly toward collapse, white dwarfs cooling slowly, neutron stars rotating with impossible precision, brown dwarfs fading invisibly through darkness, binary systems distorting space-time itself, all sharing the same galaxy, all obeying the same laws, all contributing to the long physical story of the universe. And perhaps that is the final thing stars reveal, not merely how the universe works, but how deeply connected everything inside it truly is. From hydrogen fusion in stellar cores to the atoms inside living cells, the chain never actually breaks. The night sky is not separate from Earth. It is Earth's history written outward across space and time. And as the stars continue their slow, silent evolution overhead, the universe keeps telling the same story it has told since the beginning. Gravity gathering matter, fusion igniting light, time reshaping everything. Again and again across billions of years, beneath every sky that has ever existed.